Hey guys, how are we doing? How is everyone doing? I can see the chat's popping off already. Hello. Are you guys ready for chemistry paper one? Let me know. How are you guys feeling for tomorrow? How is biology? I've been getting mixed comments about biology. Mostly the combined people found it okay, but I heard the triple paper was quite hard. Biology was all right. Yeah. Electrolysis, yes. Roy Akbari going through electrolysis today. So you'll see in the workbook the topics that I'll be going through today. It was mid, apparently. All right. Well, anyway, guys, we're done with that. We're done with bio paper one. Let's put a tick there. Well, let's put a cross. We're done. Okay, we're on session 2 now. 2 of 6 science papers. All right, we're focusing on chemistry paper 1. Don't worry about bio paper 1. All right, you've got paper 2 to catch up on if you felt that it didn't go well. But today is all about tomorrow's paper, right? So we've got a lot to get through. 5 topics in chemistry. It's a bit different to biology. Biology, we're doing 1 topic per hour, right? Here we got to cram a bit more in there per hour. So if you guys want to take part in the chat, remember to subscribe. I'll try and answer questions, but already there's 400 people in here, and the chat is just going. So I'll do my best. It is quite hard to keep up with everything. You guys should have got the workbook sent to you. This is how it looks like. We did have some people who signed up with their school emails, by the way, and we tried to send them the workbooks, but I think the school email blocked our emails. So if that is the case, then just email us at help@flashrevisionlab.com, and we'll send it to you guys. So you should have been given this workbook, a few cheat sheets, a recording of the Easter boot camp. That one is basically everything in the paper. So today we're going to be focusing on like the hot topics, the ones that come up the most. We're going to be doing exam questions as well. But if there are any topics which are not in the list, you guys have that recording to go back and basically watch me going through those topics. So I went through this during Easter. I went through every single topic. So make sure you do that, guys, if there is a topic that I don't cover today. So the aim is to cover everything using either this recording or the Easter Bootcamp recording. This live will finish at 9:30 p.m., guys, 9:30 p.m. So let me just check if I haven't missed anything before we get started. So there are some higher only topics today, guys. So if any of your foundation, I'll let you guys know. It's mostly the mole calculations which are higher only. So foundation people won't need to know that. And on the workbook, it says HT only in brackets. If it says that, you guys don't need to know that. So you can like take a break and then come back when I get back to the normal topics. If the stream goes down, guys, sometimes it does go blurry. Just bear with us. Usually it comes back. You'll be able to hear me fine as well. It's never like shut down completely before. So fingers crossed it doesn't today as well. Right. How'd you get the workbook, guys? Email us. Someone will send it to you. Okay, so this is what we're going to be doing, guys. I'm going to be going through the workbook that we sent you all. This one here. I'm going to be switching between that and the cheat sheets. So the cheat sheets are like a summary of each of the topic. We've got a combined one and a triple one. So let's go. Paper 1. So the key topics that we've got. First one, very first topic in chemistry paper 1 is atoms, elements, and compounds. Comes up every single year. There's not a year where it hasn't come up. Okay, so it'll be asked in some form. Okay, it might not be a big topic, a small topic. So let me quickly go through that. So first of all, we have 3 subatomic particles. Can anyone tell me what the 3 subatomic particles are? Let me know in the chat. So I'm going to start a table here. We've got the particle. You need to know the mass, and you need to know the charge. There we go. People are saying it in the chat already. you need to know the mass and charge of each one. All right, so first of all, we have protons. Protons have a charge of +1. How can you remember that? Because protons start with a P, because they are positive. So they're positive. They have a charge of +1. Next, we've got neutrons. Neutrons has, if you look at the first few letters, neutral. They are neutral. That means they have a charge of 0. Neutral means 0. No charge whatsoever. And then the one you're left over with is, everyone's saying it, electrons. Electrons have a charge of -1. Well done, guys. You also need to know the masses of each one. So if you look at an atom, the very middle is the nucleus. Very, very heavy. That's where pretty much all of the mass is concentrated in. So all of the mass pretty much in the nucleus, which contains protons and neutrons. Okay. So that's the heaviest part. So that's going to have the heaviest mass. They both have a relative mass of 1 because they're the heaviest. Electrons, they orbit the nucleus in shells or energy levels. And they're tiny. You don't need to know the number. You don't need to know how tiny for GCSEs. You can get away with just saying they're very small. Yeah, just saying that is enough. If you look at the spec, that's what it says that you need to know about that. Hello, Ashton. Hi. So that is the 3 subatomic particles. So whenever they mention the subatomic particles, that's what they're talking about. What else do you need to know? In an atom, the overall charge of an atom is always 0. Okay, that's because, remember, protons are positive, electrons are negative. You always have the same number of protons and electrons in an atom. So you always have the same amount of positive charge and the same amount of negative charge. So they cancel each other out. So protons equal electron number and the charges cancel out. That's why an atom overall has no charge. You might get given a chemical symbol. Every element in the periodic table has a chemical. So carbon is a C, and you have 2 numbers. You have one at the top and one at the bottom. The top one is known as the mass number. The mass number is the neutrons plus protons. So both of them added up together. So it's essentially the mass inside the nucleus. Atomic number, that's the bottom number, is the number of just the protons in the atom. All right. So just using those 2 numbers, you can figure out how many protons, how many neutrons, and how many electrons there are in any atom. To work out the number of protons, all you need to do is look at the atomic number, because that's what it is, right? If you want to work out the number of electrons, same thing again. You look at the bottom number, the atomic number, because remember, protons and electrons are equal to each other because they need to cancel each other out. So whatever the number of protons is in an atom, the number of electrons is the same. Number of neutrons, you have to get the top number and minus it from the bottom number, okay? So neutrons is the mass number minus the atomic number. You subtract the 2. All right. So all the elements you can find in the periodic table. Yeah, hopefully you guys know. You get given the periodic table in the exam. I always tell people, as soon as you get into the exam hall, do this. Mark the little staircase. So the staircase, let me show you where it goes from, is boron. You've got boron here. It's not very clear, but start a staircase like this. It has to be on the left of boron and then just go 1 across, 1 down, 1 across, 1 down, 1 across, 1 down, and keep going. And what that does is it separates your non-metals from your metals. So everything to the left are your metals, and everything to the right is your non-metals. So I tell people to do that as soon as they get into the exam hall, because you'll need to know, like you'll probably have to use it at some point in your exam. Isotopes, common question that they ask about. What are isotopes? Isotopes are atoms of the same element, and they have the same number of protons, but a different number of neutrons. So we've got a perfect example here of 3 isotopes of carbon. Carbon 12, carbon 13, carbon 14. Carbon 12, you can see here, has 6 protons. Remember, it's the bottom number. 6 electrons, because that's the bottom number. Number of neutrons, you do 12 minus 6. That gives you 6. Carbon 13, the numbers are slightly different. You still have 6 and 6 for the protons and electrons. And for the neutrons, you do 13 minus 6. And that gives you 7. Then for carbon 14, you do 14 minus 6, which gives you 8. So you do get questions on isotopes quite a lot. Right, so elements and compounds. So elements are what you find in the periodic table. Compounds are when you have multiple elements together and chemically combined. So what happens is, for example, if you have hydrogen, hydrogen is an element, oxygen is an element. Okay, they're both gases, they're both very flammable, both of them. But when you combine them together, they form a compound. Water is a H2O, right? It's a mixture, not a mixture, sorry. It's a compound consisting of hydrogen and oxygen. And as soon as you make that compound, the properties are completely different. If you think about water, water is a liquid, it's not a gas, and it's not flammable at all. So what I'm trying to say here is you can get elements and chemically combine them, and it completely changes their property. Okay, so size and mass of atoms, quite a small topic, yeah? But it's very important to know the mass of an atom. Guys, what's the mass of an atom and what's the mass of a nucleus? 2 things you need to know. Mass of an atom, mass of a nucleus. Mass of atom in meters. Not mass, sorry, my bad. Radius, size of an atom, and size of a nucleus. We've already gone through the mass, haven't we? We have, there we go, someone said it already, 10 to the minus, not 15, size of an atom is 10 to the minus 10, yes. 1 times 10 to the minus 10 meters. And the size of a nucleus is around 10,000 times smaller, 1 times 10 to the minus 14 meters. Okay, so to get from an atom to a nucleus, it's about 10,000 times smaller. And that's something it says you need to know in your spec. In your spec, it tells you that's something that you need to know. What do we have next? That was a very small section. Relative atomic mass calculation. Right, so this is a calculation and it comes up almost every year if you're triple, okay? Not as often if you're combined, but it's such an easy calculation that I just wanted to go through with you guys. Relative atomic mass of an element. So you'll see probably a table that looks like this. You'll have like an isotope, or you have the mass number of isotopes of an element, and you also have the abundance. Does anyone know what abundance mean? What does abundance mean? So they give you an element and they'll say, these are the mass numbers of different forms of this element, and this is the abundance. how common it is. Yes, exactly. It's how common it is. So imagine we had this here. We have chlorine 35. So if you have chlorine 35 and chlorine 37, so imagine we have a gas canister full of chlorine. It has 75% of chlorine 35 and 25% of chlorine 37. So these are two different isotopes of chlorine. And they'll tell you what these isotopes are, and they'll tell you what the abundance is. So that means 75% of it is this isotope and 25% of it is this. And they usually give it to you, if you look at all the past papers, they usually give it to you in this form of a table. So they'll put 35, 75% abundance, and then 37 and 25% abundance. And it's very quick, guys. The calculation is very quick. All you do is you get the mass number, multiply it by the abundance, then do the same for the bottom one, mass number, multiply it by the abundance, add them together, and divide the whole thing by 100. All right, so here's the working out. 35 times 75 plus 37 times 25, add them together and divide it by 100. Yeah, if you're not good at that, guys, go onto our website, flashrevisionlab.com, and there's like loads and loads of examples if you want to practice that. And you get 35.5 when you do that. I'm sure there's an example that we're going to go through in the workbook anyway. So yeah, just practice that. Be ready for that. Very common question. Next, we're going to go talk about two different groups, group 1 and group 7. You do need to know about group 0. It doesn't get asked that much. Group 1 and group 7 are the most common ones that get asked. Those are the ones which you need to know in detail. All right. So group 1, what's the name of the group 1 element, guys? Group 1 elements. What do we call group 1? Let me know in the chat. Alkali metal frozen straight in there. Alkali metals. And what are the group 7 metals? Not metals, sorry. What are the group 7 elements called? So you need to know the names of the group 1 elements, group 7 elements. There we go. People are saying it now. Halogens. And just to complete everything, what's group 0? What do you call the group 0 elements? I'm loving this, guys. Keep it up. Keep it up. Noble gases. I'm going to write it down here. Group 0 is known as the noble gases. They don't react. They're noble. Noble means good. They don't react because they're good. They stay as they are. So for group 1 elements, you've got lithium, sodium, potassium, blah, blah, blah. Okay. All of the group 1 elements, if you look at them, let's go here. All of the group 1 elements have 1 electron on their outer shell. Here we go. We've got lithium, sodium, and potassium here. And you can see they all have 1 electron on their outer shell. As you go down that group, so as you go from lithium to sodium to potassium, and you add it, and you react them, what happens to reactivity, guys? What happens to reactivity as you go down group 1? Increases. It increases, okay? You need to be able to explain why it increases, okay? There's a few points that you need to make. So look at this, guys. Remember, the nucleus is made up of protons and neutrons, right? I said protons are positively charged. So the nucleus overall is positive for any atom. It's always positive in the middle. And the electrons are all negative, all right? So what we get here is attraction. We get attraction between these electrons and the nuclei. Which one of these 3 outer electrons, guys, do you think is the most attracted to its nucleus? Look at the distance between them. Which one do you think is the most attracted to the middle? No, not K. It's not. It is lithium, guys. Think about magnets. Yeah, if you have magnets which are really close together, they're very attracted to each other, right? So this attraction in lithium is quite strong. But if you compare that to potassium, because the outer electron is far, it's not as attracted. So when these react, when these elements react, what they're trying to do is they're trying to get rid of that outer shell electron. They're trying to get rid of that one electron on the outer shell. The potassium one is much easier to remove. It's much easier to remove this one because it's far away and there's less attraction. So this makes potassium more reactive. Because it's so easy to remove electrons, it makes potassium very reactive. But lithium, because it's close to the nucleus, it's got a lot of attraction. We call that electrostatic attraction, meaning it is difficult to remove. It doesn't react as much. Okay? So that is a common question. Common question. It's all to do with attraction. So let's put some points down here. So as you go down the group, we can say electron, I'm going to put E minus here, gets further from the nucleus. Meaning there's less electrostatic attraction. We don't say intermolecular. Today, I'm going to tell you guys the difference between electrostatic and intermolecular. People get these confused all the time. I'll tell you guys. For now, just note this down. Yeah, so less electrostatic attraction between the outer electron and nucleus. So you say less energy, or we'll say it's easier for GCSEs, it's fine to say this, easier to remove an electron. Now, let's compare this to group 7, because group 7 elements, they get bigger as you go down the group. So look at fluorine and chlorine, and imagine bromine would be even bigger. If you go down group 7, guys, reactivity doesn't increase, it decreases. Okay, and you need to explain why. The outer electrons are still further away. So look at chlorine. The outer electron is still further away. But the difference between halogens, the group 7 elements, and the group 1 elements is that for the group 7 elements, they are trying to gain an electron. For the group 1 elements, they were trying to lose the electron. So when they react, they were trying to lose the electron, but for the halogens, they were trying to gain the electron. So now think of it this way, guys. Which one is easier? Which one's going to find it easier to take that electron in? Is it going to be chlorine or fluorine? Which one is going to find it easier to attract that electron to its outer shell? It's trying to pull it in. Yeah, that's it, guys. Fluorine, because again, it's fluorine. Fluorine is because, think about the magnets again, yeah? Positive thing is closer to the electron that's being added. So there's going to be more attraction. It's going to find it easier to add the electron. But for chlorine, because it's further away, there's going to be less attraction. It's going to find it harder to pull that electron in. So that means fluorine is more reactive. So it's the same thing happening with the size. The electron's getting further away, but this time they're trying to gain electrons. So the way that we'll change our answer is we'll say electrons get further from the nucleus. So that means there's less electrostatic attraction. From the nucleus. So it's more difficult to gain an electron. So it's just that last bit, guys. It's just that last bit that's different. It's trying to gain an electron. It's becoming more difficult to gain that electron. So that's why the reactivity decreases as you go down the group for halogen. But for alkali metals, they increase. That's what this is about. Now, in terms of reactions, guys, there's a few reactions that you need to know with alkali metals, especially. This is the one by far that gets asked the most. What happens when you add these group 1 elements into water? So they're very, very reactive reactions. Have you guys seen this in real life in school, where you add like potassium or sodium in water and then it starts like exploding? Yeah. Yes. Exactly. So what happens is the further down the group you go, the more violent the reaction becomes. What you see is the metal melts into a ball and it floats around the surface of the water. That's what happens with lithium, sodium, potassium. The ball gets smaller and smaller and smaller. There's bubbling, and then eventually it pops at the end. For potassium, there's something extra that happens. The potassium catches on fire because it's so reactive with a lilac flame. Okay, so that's the one that you need to know the most. You also need to know how to write an equation for these reactions. So potassium plus water is always forming a hydroxide. So potassium hydroxide plus hydrogen. And this is the equation that you have. If you wanted it for another group 1 element, you just swap the K for the other group 1 element. So if you wanted it for sodium, for example, this is how you change it. So if you just memorize this, then you're all good for writing the equations. You also need to know, these ones come up less, reaction with chlorine. We've got the reaction here. And the reaction with oxygen. You don't need to know the observations as much for this, but the key thing is it gets more vigorous, more violent as you go down the group. For group 7, there's a bit more you need to know. All right, so group 7 elements have 7 electrons on the outer shell. You need to know, first of all, they are all diatomic elements. That means they exist as 2 atoms bonded together. So you have F2, Cl2, Br2, I2. This is how they exist in real life, diatomic. So 2 atoms bonded together. Another thing you guys need to know is how each of these look like. You need to know how, what state they're in at room temperature and what color they're in, what color they are. So we've got here to show you guys. So we've got fluorine, for example, F2. Remember, they're all 2s, they're all diatomic. Fluorine is a gas, it's yellow, so it's yellow gas. Chlorine is a green gas. Bromine is a reddish brown liquid, and iodine is a dark gray solid, but you do see some purple vapor with it as well. You see some purple vapor being given off it. Not only that, you also need to know the color in their solution. So chlorine and fluorine are both colorless. Think of like swimming pools. Swimming pools have chlorine in them, right? Swimming pools are colorless. It's like normal water. If you were to take like a glass of swimming pool water out, it would be completely colorless, right? So putting chlorine in water doesn't change its color. Putting bromine in water makes it orange. You come across bromine in paper 2, if you guys remember, it's a test for alkenes. It's orange, so you can remember that. Iodine in solution, remember when we use iodine solution, biology paper 1 is a test for starch. It's a brown solution. Slightly different colors. So their color in solution of these halogens is slightly different to their actual colors. All right, so this is their actual colors. If you were to see these elements in their natural state, this is what they'll look like. But if you were to get these elements and add them in water, they'll change slightly. You need to know both for exams. Okay. we've explained how reactivity decreases, why reactivity decreases. You need to be able to explain why melting and boiling point decreases as well. So as you go down group 7, reactivity decreases. We've explained that. Color gets darker. You can see that here. It goes yellow, green, brown, gray, dark gray. So as you go down, the color gets darker. You don't need to explain why. Boiling point increases. Yeah, because you've got a gas, then it goes liquid, then it goes solid. So next one is probably a solid as well. Astatine is probably a solid as well. You do need to explain why it does that. It's all to do with bonding. And we're going to see this in the second topic as well. As you go down the group, you get more electrons in the atoms and in the molecules, yeah? Because you're starting off with really small atoms. So this is fluorine. Then you've got chlorine, which is slightly bigger. It's got more shells, it's got more electrons. Then you got bromine, which is even bigger, okay? And then you got iodine. So what's happening is the bigger these molecules are, the more electrons they have. This is where we talk about intermolecular forces. You only talk about intermolecular forces when you're talking about molecules. Intermolecular forces. So as you go down the group, there are stronger intermolecular forces, meaning more energy is needed to break those forces. Okay, we are going to explain this again in the next part, guys. So if you still don't get it, don't worry. I'm going to do it again. I'm going to tell you guys the difference between electrostatic and intermolecular again. Now, chemical reactions. We've got simple reactions here of these group 7 elements reacting with hydrogen or reacting with a metal. These don't get asked much. What does get asked a lot is these displacement reactions. So when you have a group 7 element, it can react with a compound. And what will happen is the more reactive group 7 element will replace the less reactive group 7 element. So you see here, we've got potassium bromide and we've got chlorine. When those two react, the chlorine will replace the bromine because chlorine is more reactive than bromine. It's higher up. It'll replace it, and what you end up with is potassium chloride and bromine being formed. This is called a displacement reaction. If you were to do the same, but with potassium chloride and bromine, nothing will happen because bromine is less reactive than chlorine. So it will not replace the chlorine. Okay, if it's less reactive, it won't replace it. There'll be no reaction here. So when you see these, just take a look at the elements and just decide, is it more reactive? Is it not reactive? Is this going to work or not? All right. So in terms of topic 1, those are the topics that I wanted to go through. Okay. So we could go through questions now, but what I want to do is jump to topic 2 now. I want to go through the theory in topic 2 and then do questions on both of those. Just because, remember, there's 5 topics that we need to go through, and there's only going to be like 4 sessions, 4-hour sessions. So I'm going to jump to the next topic, and we'll come back and do these questions after we do this. So I'm jumping to topic 2. We need to talk about ionic bonding and covalent bonding. All right, so there are 3 types of bonding you guys need to know for chemistry. Let me write that out here. I'm going to do a summary here. There is ionic bonding. There is covalent bonding, which is the one that you need to know the most about. And there's metallic bonding, which doesn't get asked much because there's not much to know about it. Yeah, but it does come up. So difference between them, guys. How can you tell which type of bonding there is? This is what I want you guys to do in the exam tomorrow. You're going to get given a compound first, and they're going to ask you about melting points or something like that. If they do, you have to first identify which three of these does it belong to. How do you know something's ionic, guys? How would you know? Tell me in the chat. How would you know something has ionic bonding? You look at the elements involved. Yes. Metal plus a non-metal. Well done, guys. So remember I told you at the start of the exam, draw that little staircase. If you have a metal and a non-metal within it, it means it's ionic. So sodium chloride, calcium oxide, potassium bromide. You have a metal, you have a non-metal. So this is metal plus a non-metal. What about covalent bonding? How do you know when you have covalent bonding, guys? That would be, there we go, non-metal with a non-metal. So that would be something like carbon dioxide. Water is hydrogen and oxygen, two non-metals. What else do we have? Methane is carbon and hydrogen. Yeah, so if you have two non-metals, it's covalent bonding. So non-metal plus non-metal. And then you've got metallic bonding, which is easy. That's just metals, right? So that's just a metal bonding with itself. Ionic bonding involves the transfer of electrons. Transfer of electrons. So electrons are jumping from one atom to another. So one of these, the metal always loses electrons. The non-metal always gains electrons. Covalent bonding is not the transfer of electrons. It is the sharing of electrons. Sharing of electrons. Okay, so let me jump to the cheat sheets so I can show you a bit more on them. You figure out how many electrons are lost or gained, okay? So the aim of these atoms is to get a full outer shell. It always wants to get a full outer shell. Why? Because it makes them more stable. Yeah, they're happier that way. So if you have something like this, like sodium, it's got one electron on its outer shell. Remember I told you it's trying to lose electron. The reason why is because it's going to be more stable without that outer electron. So look at this one. The outer electron is gone. Now it's more stable. But now that you've removed an electron, we've basically made the charges unbalanced. Remember I told you in an atom, the number of protons and the number of electrons are always equal to each other, right? Now imagine we took away one of those electrons. Now all of a sudden, there's more protons than electrons. So the whole thing's going to be positively charged. So if you take away an electron, it will become positively charged. And you show that by putting a square bracket around it and putting a plus on it. If it's something that's a non-metal, so like oxygen, the opposite happens. It gains electrons. So like group 7 elements, they gain electrons. Remember, they're trying to get a full outer shell. Right now, it's got 6 electrons in its outer shell. It wants 8. Remember, the first shell holds 2. The second shell holds 8. The third shell holds 8. So for this to be stable, it needs to gain 2 electrons. Now imagine we have a certain number of protons and electrons. They're both equal in the atoms, but we've just added 2 extra electrons in them. Electrons are negative. So we've just made it twice as negative. So the whole thing becomes 2 minus. So we put our square brackets around it and put a 2 minus there. So if you just want to memorize it, this is what you can do. Okay, so remember that periodic table? I told you to draw a staircase on it, right? The other thing you can do if you want is go to group 1. So look at the numbers at the top. Go to group 1, put a +1. Go to group 2, put a +2. Let me write these a bit clearer. Because this tells you what charge the ions are in these groups. Group 6 is -2 and group 7 is -1. Okay. I'll put group 3 in here as well. In your spec, it says you don't need to know group 3, but aluminium does come up sometimes. So that's +3. Okay. Group 4, 5, and 7, they don't form ions, so you don't need to know those. Okay. So these are the types of ions that each group forms. So you can just quickly write that in your periodic table. So when you get into the exam hall, draw your staircase. Group 1, put +1. Group 2, put +2. Group 3, put +3. Skip out 4 or 5. And on 6, put -2. And group 7, put -1. That's going to tell you the charges of those ions. Okay, so we have sodium, which is in group 1. That forms Na+1. We just call that Na+. We've got chlorine, not chlorine. So we've got oxygen. That's in group 6. That forms O2-. All right. Now what happens is both of these are oppositely charged. So they're like magnets. They attract each other now. Okay. Remember, they got attraction, electrostatic attraction. And that's what gives you your ionic bond. So look at this example here. We've got lithium. Lithium has 1 electron in its outer shell. We've got fluorine, which has 7 electrons in its outer shell. What's the easiest way for both of these to get full outer shells? Well, the fluorine can take the electron from the lithium. If it does that, they're both going to be happy now. They're both going to be stable because now lithium is going to have a full outer shell. It's 2 because it's in this first shell. Fluorine is going to have a full outer shell now because it's got that extra 8th electron. And you can see both of these are stable. But what's happened is you have oppositely charged ions now, and they're attracted to each other like magnets. This is electrostatic attraction. Whenever it's something positive and something negative, attracting, electrostatic attraction. That's what I want you guys to remember. All right. So for ionic bonding, we talk about electrostatic attraction. Let's write that down here. Now, how is this different to covalent bonding? Covalent bonding, the diagrams look different. There's no square brackets. There's no positives and negatives. It kind of looks like a Venn diagram. Yeah. Covalent. Venn. V-E-N. Venn diagrams. Yeah, it looks like a Venn diagram. I know there's an extra N, but you know what. Now, these ones are sharing electrons. They still have the same aim. They still want full outer shells, but they're sharing electrons in order to get that. So hydrogen looks like this. Chlorine looks like this. So let me draw one from scratch here. Let's say we have, I don't know, let's do fluorine, okay? We're going to draw a Venn diagram. And we're only going to draw the outer shell electrons, okay? So in covalent bonding, you only show the outer shell electrons. In fluorine, it is in group 7. Therefore, it's got 7 outer shell electrons. So we have crosses for one, and we have dots on another. So we have 7 crosses, 7 dots. We need both of these to get full outer shells. How many outer shells does it need? How many outer shell electrons does it need? It needs 8. Right now it has 7. So what they need to do is they need to share 1. If you look at the left-hand side, it's got 7 electrons. It needs to get to 8. So it needs to share one of the dots in order to get that, right? So anything that needs to be shared, you put in the middle. On the right-hand side, again, you have 7 electrons. You need 1, so you need to share 1 with the crosses, with the left-hand side. So I'm going to take one of these crosses, and I'm going to put it in the middle. Now, what are we left with? On the left-hand side, we're left with 6 crosses. So I'm going to put 6 crosses here. 1, 2, 3, 4, 5, 6. I'm not putting it in the middle bit because the middle bit is only for sharing. We don't need to share these because now the right-hand side has enough electrons. The right-hand side has 6 dots left. So we're going to get those 6 dots. 1, 2, 3, 4, 5, 6. And we're going to do that. And you can double check now. 1, 2, 3, 4, 5, 6, 7, 8. This one is happy now. It's stable. It's got 8 electrons. This one also has 8 electrons. It's happy. They're both stable. So what we've done is we've shared the electrons and made both atoms stable. It's happy now. That's covalent bonding. Okay. And attraction between the nuclei and the electrons, which holds everything together. So ionic bonding. Let's go back to ionic bonding. There's one type of ionic compound that you can have. Okay, so ionic compounds. We're talking about electrostatic attraction, and it's between the oppositely charged ions. Let me show you examples of ionic compounds. So ionic compounds have high melting and boiling points. This is what they look like. Okay, so remember, an example would be sodium chloride, which is Na plus minus. And look what's happening here. You've got sodium ions and chloride ions. And they're basically arranged in this lattice structure. A lattice structure is like a cube structure. And it goes like this. You've got chlorine, sodium, chlorine, sodium, chlorine, sodium. They're alternating. And they're all held together. Remember the attraction? It's like magnets. They're all stuck together because the positive and the negative charges are creating electrostatic attraction. Remember, something positive, something negative is electrostatic attraction. That's sticking everything together. Another thing is that these ionic substances, compounds, they don't conduct electricity when they're solid. These do not conduct electricity. What do you need, guys? Here's a question for you guys. What do you need for something to conduct electricity? There's two things that it could have, all right? If a substance conducts electricity, what does it need to have? Let's see what you guys are saying. It needs delocalized electrons or free moving ions. Good. One of those two things. Delocalized electrons or free moving ions. Which one is it for this? Right now, there's nothing. Yeah, when it's a solid, there's nothing. There's no free moving ions. Delocalized electrons, all the electrons are stuck within the atoms. But if you were, there we go, I'm seeing the right answers. If you were to melt it, basically go from this cubic structure to all the ions just floating around, right? Because in liquids, the particles are like all flowing, right? So now the ions are free to move. So we have free moving ions. So when this is molten means melted to liquid, it can conduct electricity. It can also conduct electricity when it is aqueous. What does aqueous mean? You get the solid and you dissolve it in water. So for ionic compounds, they only conduct electricity when they're molten or aqueous. Okay, so what have we learned so far? We have learned ionic compounds, they exist as a lattice structure. Let me put it up here. So that's that cubic structure. We have learnt that they have high melting and boiling points. I'm going to put just BP, high melting and boiling points. The reason for that is because they have strong electrostatic. So to melt this, you need to break all of the ionic bonds, don't you? All of that attraction, all of these lines between it, you need to break those. These are extremely strong. So trying to break them needs a lot of energy. So that means it's going to be hard to break. You need a high melting and boiling point. High melting boiling point. So the explanation for that is because strong electrostatic attraction. The other thing is they conduct electricity only when molten / aqueous. If they are solid, they don't conduct electricity. And you need to remember that's because of free moving ions. No, not delocalized electrons. You'll get it wrong. For ionic bonding, if you say delocalized electrons, you'll get it wrong. Okay? So, covalent bonding, there's a bit more to it. There's 3 types of covalent structures you need to know about, guys. So I'm going to draw 3 arrows here. We have 2 main ones, and then you got 1 which isn't asked that much. Let me spread these out a bit more, actually, because we're probably going to end up writing more. We have yeah, there's both triple and combined, guys. Everything I've said so far is triple and combined. Okay, I'm seeing some correct answers here. So first one is simple molecular substances. So you can either have simple molecular substances, you can either have giant covalent substances, or polymers. Okay, and we're going to go through all 3. Simple molecular substances. Molecular. That word molecular. This is when you've got substances existing as molecules. Remember what molecules were? Molecules are 2 or more atoms bonded together. So in chlorine, remember chlorine is diatomic. You got a chlorine atom, and they're held together by a covalent bond, yeah, because it's a non-metal. And it makes this molecule. Now, between 2 different molecules, you have a different type of bond. So between the atoms, you've got covalent bonds, which are very, very strong. Between the molecules, you have intermolecular forces. Inter means between, molecular means molecules. So you only get this in simple molecular substances. Intermolecular forces. Forces are extremely weak. They are so easy to break, which means you don't need a lot of energy to break it. So remember in that big cube I showed you, I said you need a lot of energy to break those ionic bonds, right? Intermolecular forces, you can break these very, very easily. So that means they have a very low melting and boiling point. So the explanation is weak intermolecular forces between molecules means they have low boiling and melting point. So usually these substances are liquid or gas at room temperature. And as the molecule gets bigger, the boiling point increases. And I explained earlier with the halogens, because the molecules get more electrons, they have stronger intermolecular forces. Do these conduct electricity? No, they don't conduct electricity. Simple molecular substances don't conduct electricity. Why is that, guys? Let me know in the chat. Why do simple molecular substances not conduct electricity? Remember, what do they need? 2 things. What do they need? No delocalized electrons, good, free moving ions. There we go, guys. You guys are doing well. Smashing it, guys. So simple molecular substances, we can say have low melting point and boiling point. This is where we talk about weak intermolecular forces. So remember the difference. Electrostatic is between something positive and negative. Intermolecular means between molecules. It's literally in the name, intermolecular. You pretty much only talk about intermolecular forces in covalent bonding, in some types of covalent bonding. They don't conduct electricity. Then you have giant covalent substances. This is when we need to start talking about the allotropes of carbon. Giant covalent substances don't usually have intermolecular forces. They're just connected with covalent bonds throughout the whole structure. So every single atom is connected with very, very strong covalent bonds. Covalent bonds are so hard to break. Yeah, they're the strongest type of bonding you can get. So you need a huge amount of energy to break these. So they have extremely high melting and boiling point. So this is silicon dioxide, very high melting and boiling point here. And then you've got diamond. Diamond's another example. It's very strong covalent bonds. You need a lot of energy to break it. And graphite as well, very high melting and boiling points. So giant covalent, we can say high melting point and boiling point. Why? Because they have strong covalent bonds. We're not talking about intermolecular here because they're not existing as molecules. They're just this huge structure of loads of covalent bonds, strong covalent bonds. Do they conduct electricity? Some of them do, some of them don't, okay? So let me go through that. Does diamond conduct electricity? No, it doesn't. Diamond does not. Diamond is made up of carbon. Carbon has 4 electrons on its outer shell. That means it can form 4 bonds, 4 covalent bonds like this with other carbon atoms, okay? In graphite, the carbon doesn't form 4 bonds. It forms 3 bonds. So remember, it has 4 electrons on its outer shell, and it's only forming 3 bonds. So that means there's an extra bond here that's not getting used for bonding. And you can see this because graphite is like this hexagonal ring, it forms 3 bonds. But for diamond, 1, 2, 3, 4, it forms 4 bonds. So that means there's this extra electron here, which isn't fixed within the structure. So this one can go and float around. That's delocalized. That electron is delocalized. So that means graphite can conduct electricity. And you can remember that because it's got an E in it for electrons. Yeah, it's got free moving electrons, delocalized electrons, and charge can move through the structure. Okay. Graphene. Graphene is a single layer of graphite. So graphite is multiple layers of these hexagonal rings. Graphene is just one of these layers. So again, it can conduct electricity. And then we've got these fullerenes, which are basically molecules which have like hollow shapes with them. So you can have this Buckminster fullerene. Buckminster fullerene is just loads of carbons in the shape of a ball, a sphere. It's C60. That's the molecular formula for Buckminster fullerene. And you can also have carbon nanotubes here, which are basically carbon atoms in the form of a very long tube. They also conduct electricity and heat because they have delocalized electrons. Okay, so it varies whether they conduct electricity or not. Then you've got polymers. Polymers. Think of polymers as very, very big molecules. Okay, so they have intermolecular forces as well, but the intermolecular forces are very, very strong, very strong. So they have high melting and boiling points because their intermolecular forces are strong. You can think of them as molecules. They're very, very big molecules, okay? So polymers are very, very big molecules. So they have intermolecular forces, but the intermolecular forces are stronger when compared to a simple molecular substances. And then we've got metallic bonding, which I'm going to just quickly go through, and then I'm going to give you guys a break. Metallic bonding is different. It's the one that gets asked the least. It's basically just loads of metal ions. So imagine all of these metal atoms and their electrons coming off it. It's loads of these positive metal ions surrounded by a sea of delocalized electrons. So I always tell people to imagine like a river. Okay, so there's a river. In the river, you have these stepping stones, which are fixed. That's the positive metal ions. And then you have the water. The water is the electron. It's a sea of delocalized electrons. The electrons can flow through the positive ions. That's why metals can conduct electricity. That's why they can conduct heat, because they have delocalized electrons that can carry a charge, and it can carry heat as well. So what can we say about metals? We can say there's positive metal ions surrounded by a sea of delocalized electrons. All right, guys. So we have just gone through the 3 types of bonding, and we've done everything on atoms. So topic 1 and topic 2, we've just gone through a lot of that. So I'm going to give you guys a 10-minute break, and then we're going to try some questions on these 2 topics, guys. All right. So remember, if I have missed out any topics that you guys wanted to go through, you do have the Easter Bootcamp recording as well that you guys can watch. Well done for sticking through that. That was a very content heavy, guys. But I'll see you back in 10 minutes. So we'll be back at 6:40, guys. See you in a bit. All right, guys, welcome back. Welcome back. I hope you guys are finding this live useful. So we're going to try some exam questions now. So on the workbook, guys, we're going to go through topic 1 exam questions. And then we're going to do topic 2 ones, and then I'm going to start on topic 3 in this session as well. So topic 1 question. First of all, what's the approximate radius of a carbon atom, guys? What do you guys think the answer here is? 0.1 meters is definitely not that. 0.1 meters, 10 centimeters. Imagine if atom was that big. 0.1 millimeters is small. 0.1 nanometers. Does anyone know what a nanometer is? Nanometer. How many meters is 1 nanometer, guys? There we go. Someone's got it. 1 times 10 to the minus 9 meters. Yeah. So that's 1 nanometer. So 0.1 nanometer is 1 times 10 to the minus 10 meter. And remember, that's what I told you needed to memorize as the radius of an atom. So the answer here is 0.1 nanometer. Yes. Micrometer. Someone said micrometer. No, that is 1 times 10 to the minus 6 meters. 1 micrometer. Right. We've got an atom of carbon here, 6 marker. And it says describe the atomic structure of this carbon atom. What are things we can say here, guys? We just need to describe it. You should include the number of electrons, neutrons, and protons. What do you guys think we can mention here? There are 2 electrons, there are 4 electrons. Yes, so we can say 6 protons. So there are 6 protons, 6 electrons. Yes, well done, guys. And how many neutrons? 8 neutrons. Let's just double check. 1, 2, 3, 4, 5, 6, 7, 8. 8, exactly. What loads of people would have done is they would have assumed it's normal carbon and they would have gone to the periodic table. Normal carbon usually has 1 proton, 6 protons, 6 neutrons, and 6 electrons, usually. But this is an isotope of carbon. So it's actually 8 neutrons here. So loads of people would have put 6 there, thinking it's just a normal carbon atom. So that gets you a few of the marks, but you also need to mention where they are. So you can say neutrons and protons are in the nucleus, and electrons orbit the nucleus. Yeah. And we can say it orbits the nucleus in shells. That is enough to get all the marks there. Yeah, so 6 markers, guys. Sometimes you need to write loads, sometimes you don't need to write that much. This one, you don't need to write much because it's just asking you to describe one. All right, here we have graphite, structure of graphite. Remember the hexagonal rings. How many bonds does each carbon atom have in graphite, guys? Quick answer here. Let me know in the chat. There we go. 3. Yes, 3. What type of bond holds the carbon atoms together in graphite? You guys should know this. Graphite is carbon. Carbon is a non-metal. Non-metal. So what type of bond is it? It is covalent, guys. Well done. Lubricants allow objects to slide over each other easily. Suggest why graphite can be used as a lubricant. Why can it be used as a lubricant? Because it exists as layers, right? These layers can easily slide over each other. So that means it can be used as a lubricant. The layers slide over each other. Nice. Next one, we have 2 structures representing allotropes of carbon, 1 line. So which one of these? So what do we have here? Which one do we have here, guys? Draw a line. Diamond at the top. Yes. Diamond. Remember, that's that tetrahedral shape we say. Buckminster fullerene is the one that looks like a football. Yep. Graphene. No, graphene is the hexagonal rings. One layer of hexagonal rings. And carbon nanotubes is the tube of hexagonal rings. Nice. Well done, guys. Next one. Discoveries in chemistry led to a better understanding of atomic structure. Atoms were originally thought to be tiny spheres that could not be divided. The plum pudding model was then developed. Guys, what is the order of the scientists in the history of the atom? I put a memory trick here today. DJ red blood cell. DJ RBC. What do we have? Yes, everyone's seen it. Everyone's seen that. What do we have? We've got Dalton first. John Dalton. Then we've got J.J. Thomson. Then we've got Rutherford. Then we've got Bohr. And finally, we've got Chadwick. Okay, remember that order. You don't need to memorize the dates, just remember the order. Now, describe the plum pudding model for 2 marks. What do you guys think we could say here? For 2 marks, describe the plum pudding model. Ball of positive charge with negative charge electrons within it. Perfect answer there. So a ball of positive charge with negative electrons embedded within. Next question. Atoms contain electrons, neutrons, and protons. Write these 3 in order of their discovery. What was discovered first? First one was discovered by J.J. Thomson. Protons first? Not protons first. Not protons first. Electrons first. Yes, J.J. Thomson. We got electrons. Then we've got protons. That was after Rutherford. And then we have neutrons, which was by Chadwick. Neutrons are the hardest one to find, guys, because they're neutral. So it's hard to identify them. You can't like use charge to try and find them out. That's why they were found the last. Very few atoms of the element tennessine have ever been identified. The atomic number of tennessine is 117. Predict the number of outer shells in an atom. Use the periodic table. Does anyone have a periodic table on them, guys? Try and find tennessine. TS. I believe it's in group 7. Thank you. Easy short. Group 7. That means the number of outer shell is 7, right? And the reason for that, you say it's in group 7. Tennessine was first identified by a small group of scientists in 2010. Suggest one reason why it was not accepted as a new element by other scientists until 2015. What do you guys think there? So some people discovered it in 2010, but people did not accept that it was a new element until 5 years later. Yeah, no peer review. It clearly says a small group of scientists. They did that on purpose. They wanted you guys to see that. So like, imagine just 3 scientists have just said, oh, there's this new element that we just discovered. Put it on the periodic table. People might not believe them. They need to double check that it's correct. It needs to be peer reviewed. So there was no peer review. It takes time for peer review. So we can say it needed peer review. So other scientists needed to go and check their work to make sure it was valid. You can't just go and believe them. Here we go. Relative atomic mass. Remember I said this was quite common. You get given the table of mass number against abundance. I just tell my students to literally just write the working out here. Remember, you multiply the mass number by the abundance, multiply the mass number by the abundance again, and add them together and divide that whole thing by 100. Has anyone got the answer? So 6 times 7.6 plus 7 times 92.4 divided by 100. Yes, guys, most of you have got it. 6.9 is what you should be getting. I'm glad no one said, I haven't seen anyone say the full answer, which is good. I think the full answer was 6.924 or something. It says give your answer to 1 decimal place, which means if you write this, you lose a mark. So the answer is 6.9. Next, periodic table. Sodium and potassium are in group 1. One similarity and one difference between the electronic structures of sodium and potassium. What do you guys think? One similarity. They're both in group 1. And one difference. More shells. Yes. So we would say that potassium has more shells. That's good. Similarity, they all have, someone said they have 1 electron. That would not be right. You have to say they have 1 outer electron. They all have 1 outer electron. Yeah, because they're all in group 1. They all have 1 outer electron. Nice. Group 1 elements react with water. Give 2 observations when potassium reacts with water. I told you guys this when we did the group 1 reaction with water. What can we say? 2 points we can say. There's quite a few you can say here. Someone said smoke. I wouldn't say smoke. You won't get a mark for smoke. Fizzing, you can get a mark for. Bubbles, you can get a mark for. Yes, because it releases hydrogen. Fizzing is fine. Effervescence is also that same mark. So that all is included in 1 mark. Floating around, yes. Moves around, melts, gets smaller. Lilac flame. That is only for potassium, yeah? All the other ones don't produce a flame. Only lilac flame for potassium. Well done, guys. Potassium hydroxide is a solution produced when potassium reacts with water. Okay, so potassium plus water forms potassium hydroxide plus hydrogen. Okay, like I told you earlier, we need to balance this as well. So we put a 2 here and a 2 here. What is the color of universal indicator when added to potassium hydroxide solution? So once you get this potassium hydroxide solution and you add universal indicator, what color will it go, guys? Purple. Yes. Why? Why will it go purple is the question. Because it's an alkali. That's why they're called alkali metals, by the way. That's why group 1 are called alkali metals, because they form alkali solutions when you add them to water. And we're going to talk about acids and alkali in a bit as well. Next one, we have group 0 elements. Remember the noble gases. Plot the data. We need to plot this data on figure 1. We've got a graph here. We need to plot the data. Okay, so let's do this. Let me do this as well. And you guys can try. So we've got 2, 0.2. So each square is 2. So 2, 0.2 is going to be here. Then we've got 10, 0.8. Going to be here. We have 18, 1.6. I heard you got loads of graph questions in biology. Is that right, guys? Did you have to plot one for biology? Next one is 54, 5.4. 54 is around here. And 5.4 is going to be around there. Yeah, I guess it depends on what which paper you did. 86 is 9.1. 86 is around here, 9.1. 86, 9.1 is here. Okay. So I've plotted it. It hasn't told me to draw a straight line through the origin or draw a line of best fit or anything like that. Okay. Estimate the density of krypton. Krypton is 36. So we need to go on this graph. So we do actually need to draw a line of best fit. So you'd get your ruler, guys, and you draw a line of best fit to get this trend, because that's going to help you work out what krypton is. So I think, let me rotate this a bit so that it looks right. Something like that. So whenever you get a line of best fit, guys, just extrapolate. It doesn't matter how far you go. Some people just stop from point to point. I just tell people just go straight through. Doesn't matter if it goes over, yeah? Because you never know what they're going to ask you. Well, you do know in the next question. Estimate the density of krypton. Krypton is 36. So we need to go to 36 here. So 36 is around here. And we need to draw a line that goes upwards and basically read off what that is. Can anyone read that off in their graph? Has anyone plotted this and figured out what it is? Yeah, around 3.6 is fine. 3.6, 3.4, 3.8. So it's all about how you draw that line of best fit. There is a range, guys. It's not just one single answer. The mark team says between 3 to 3.8 is acceptable. Okay, so 3.6 is what most of you are doing. So that's good. Well done, those of you who got that. Elements in group 7 are called halogens. The more reactive a halogen can displace a less reactive halogen. Which combination of solutions produce a reaction when mixed? So remember, you need a more reactive reacting with a less reactive one. What do you guys think the answer is here? So does chlorine react with potassium fluoride? Will this replace it? We are going through practicals. Practicals come up in topic 4, all the way in topic 4. There's 2 practicals I want to go through. B, people are saying B. It is B. Remember, you need a more reactive one and replacing a less reactive one. Chlorine is more reactive than bromine, so that will replace it. Chlorine is not more reactive than fluorine, so that won't work. Bromine is not more reactive than fluorine. That's not going to work. Bromine is not more reactive than chlorine. That's not going to work either. Which of the following describes the trend going down group 7? You guys should know this. As you go down group 7, what happens to mass, relative molecular mass, and boiling point? So the MR and boiling point. MR is always going to go up as you go down the group because it gets more protons, it gets more electrons. Which one is it? Relative molecular mass and boiling point increases. Yeah, remember, they get stronger intermolecular forces. Amazing. We've done all the topic 1 questions, guys. Let's jump to the topic 2 questions now, all to do with bonding. Describe the structure and bonding of diamond for 3 marks. What do you think we could say here, guys? Structure of diamond. Let's go. Let's go. Making good progress here. How are we doing for time? 20 minutes in. Okay, cool. We'll do a bit of this and then we'll jump to topic 3. All right. Someone saying 4 covalent bonds. Perfect. No one has said what type of structure it is. Remember, it is giant. It's a giant covalent structure. You get a mark for saying that. So you can say it's a giant covalent structure. And then someone else said 4 bonds. Yeah, so each atom forms 4 bonds with other carbon atoms. To get that extra mark, we got to say what type of bond they are. I'm going to say covalent bonds. Although you'll probably get the mark for saying covalent structure. But just to be safe, I'm going to put 4 covalent bonds with other carbon atoms. And that should get you 3 marks there. Next question. Why does diamond have a very high melting point? What's the answer here, guys? Why does diamond have a very high melting point? So, strong bonds, 1 mark for saying that. 1 mark for saying strong bonds, yeah? So we can say covalent bonds are strong. What else can we say? Need a lot of energy to break. Yes, when it's a question about asking about melting and boiling point, you always need to talk about energy to break. So you can say a lot of energy is required to break the bonds. That's enough for 3 marks. Well done. Can you have the mark scheme? Yes, guys, we're going to send you guys the mark schemes. Straight as soon as the live finishes, we're going to send you guys the mark schemes. We did that for biology as well. Don't you worry. What's this name? What type of molecule is this? I'm hoping everyone knows. It's a fullerene. Whenever you've got a sphere or a ball, it's a fullerene, okay? Graphene is the hexagonal rings. Nanotube is a tube. And a polymer is those huge molecules, those very long molecules. Molecules such as C70. So they've come up with something new. And this is the thing, guys. In an exam, they will always come up with something that you've never seen before. Yeah? There's always application questions. Yeah? Apparently in biology, there's something about a goose or something, geese. And then for triple, something about vapes as well. You guys have never learned that because it's not in your spec, right? But they will always introduce something brand new that you've never seen. And what you need to do is you need to apply your knowledge. You need to use what you already know and figure the answer out. C70, you've never seen before, right? Because I told you Buckminster fullerene is C60, right? But let's see what they say. Molecules such as C70 can be used in medicine to move drugs around the body. So just one reason why C70 is suitable for this use. What can you say here? Someone said high surface area to volume ratio. Yes, it can encapsulate. Yes, it's hollow, so it can encapsulate. It can hold a drug within it. Yeah. So we can say it is hollow, so can encapsulate the drug. Nice. No, it's not triple. This is for everyone. This we're going to come back to once we've done quantitative chemistry. There's a calculation. We haven't done moles yet. We're going to do that straight after this. Why has diamond got a melting point? We've done this. Same 3 marks. Exact same answer. Maybe try this at the end of the live, guys, if you want to try and recap what you learned. We're not going to do that again. Here we go. Ionic bonding. Remember, the first thing you guys need to do, figure out what type of bonding it is. I've given it away already. Sodium chloride. Go look at your periodic table. Look at what sodium is. Look at what chlorine is. Sodium is a metal. Chlorine is a non-metal. What's a metal plus a non-metal? It's ionic. The other clue here, chloride ion, sodium ion. Explain the conditions needed to make sodium chloride conduct electricity. So when does an ionic compound conduct electricity? Seeing the answers. No delocalized electrons. Please, guys, if there's one thing I want you guys to take, ionic bonding doesn't have delocalized electrons. Delocalized electrons you mentioned for metallic bonding and graphite and graphene. Yeah, not for ionic bonding. It's because the ions are free to move. So it needs to be molten, which means melted to liquid, or aqueous. Aqueous means dissolved in solution, right? And what does that do? That makes the ions free to move. Not delocalized electrons. Ions are free to move. If the ions are free to move, it can conduct electricity. All right, so you get a mark for saying molten, you say a mark for saying aqueous, and you get a mark for saying the ions are free to move. Yep, and they can carry a charge. If you want to add an extra point, yeah, it can carry a charge. But we've already got the 3 marks for this one. But if it's a 4 marker, you can say can carry the charge or a charge. Cool. Slow mode, please. Remember, you can go back to the stream, yeah? You can rewind if you guys didn't catch something I said. This is a metal. All right, this is a good question. These are good questions because they're comparing why ionic bonding conducts electricity. This is sodium. What type of bonding is this, guys? Is it ionic, covalent, or metallic? What do you guys think? Metallic, yeah. So you go to your periodic table, you see sodium is a metal. So we need to think to our metallic bonding. Remember I said it's like the river with the stepping stones in it? The gray bit is the river, it's the water, it's the electrons. And these are the stepping stones, okay? Why does it conduct? Well, it's not asking about electricity, it's asking about thermal energy. Thermal energy is just heat. It's the same thing. This is when we talk about delocalized electrons. So they have delocalized electrons, which, what's everyone saying? Now, it's not carry a charge. That was for conducting electricity, would say it can carry a charge. Here, it's not carrying a charge. What is it carrying instead? Let me see the chat. What is it saying? Carry energy. Yes, it transfers energy, heat energy more specifically. So have delocalized electrons, which can move and transfer energy through the structure. So be careful. See what they're asking for. Here they're asking about thermal energy. They might ask about electricity, conducting electricity. Then you'll talk about transferring charge if it's about electricity. Well done, guys. This question is about structure and bonding. Which 2 substances have intermolecular forces? Okay, another good question, guys. Which one has intermolecular forces out of these? What do you guys think? Remember, molecular means it has to exist as molecules. Water, yes, water, H2O. You got tiny H2O molecules. Diamond, we know it's not. Diamond, we know that it's giant covalent, so it's not molecules. Magnesium is a metal, so it's not going to be that. That's metallic bonding. Sodium chloride, that's a metal and a non-metal, so that's not going to have it. Polyethylene, that poly tells us is a polymer. Remember what polymers are? Polymers are huge chained molecules. So they are molecules, and they've got very strong intermoleculars between them. So it would be polyethylene. Those are the 2 answers there. Okay, I think I'm going to move on to the next one. Remember, you are going to get the mark schemes to answer the other questions here. I will move on to quantitative chemistry here. Okay, so topic 3, quantitative chemistry. This is all the calculations, guys. Calculations. Some people love them, some people don't. Very common thing is to work out relative formula mass. My nightmare, says someone. Then we're going to talk about moles. This is where the foundation guys can take a break, by the way. It doesn't come up in foundation. Yeah? Because it's a HT only topics, only higher. So if you guys are in foundation, when I jump to moles, you guys can switch off and do your own revision. Same with this amount of substance in equations. You guys can take a short break. So let's start with relative formula mass. This is something that everyone needs to know. All right, so it's calculations. Relative formula mass, you basically add up all the relative atomic masses of the elements. So in your periodic table, you'll have an element. You'll have the top number and the bottom number. The top number here is the relative atomic mass. If you want to find the relative formula mass, which we call the MR, you just need to add up every single relative atomic mass of that element, of the elements in it. You just add them up, guys. Okay, so let me give you guys some examples. Where do I have space? So I've got space here. Yeah. Okay, so let's say find the MRs of the following. Let's start straightforward. We've got H2O. All right, H2O. So that means 2 hydrogens, 1 oxygen. So you go to your periodic table. Hydrogen looks like this. Oxygen. What's the numbers for oxygen? I think it's 16 and 8. Yeah. And they'll give them to you. Usually they give them to you in the exam anyway. They'll say what they are. And you'll see when we do the exam questions. So what you'll do is 2 lots of hydrogen. So 1 plus 1 again plus 16, which is equal to 18. Well done, guys. Let's try another one. Let's try... sodium hydroxide, NaOH. Can anyone tell me what sodium is? I don't remember off the top of my head. I do know what oxygen is. So oxygen is 16, hydrogen is 1. Sodium is 23. Yes, it is. Thank you. 23. Okay, so you're just going to do 23 plus 16 plus 1. 40. Yes, it is. Okay. A really, really hard one. If you guys want, as hard as it probably gets. Let's think about this. NH4 to SO4. For those of you who want a tricky one, try that one out. It shouldn't get harder than this, guys. Okay. When they have a bracket, sometimes you just need to multiply what's in the bracket. Okay. So N is 14. Can someone tell me what S is? I think it's 32, but I don't remember. Oxygen is 16. S is... This is for everyone. This type of question is for everyone. 32. Yeah. Okay. I think you're right. Can anyone figure out what this one is? So we've got nitrogen, 1 nitrogen plus 4 lots of hydrogen. So it's 1 plus 1 plus 1 plus 1 times by 2, because there's a 2 on the outside. We're going to times that by 2. Then we're going to add the S, which is 32, plus 4 lots of oxygen. Wow, you guys are amazing. I'm seeing the correct answer. Put that in your calculator and you should get the answer here. 132. Smashing it, guys. Well done. Well done. Well done. Okay. Cool. So before we go on to moles, guys, let's just try one of these. So then after that, the foundation guys can take a small break before coming back. Do we have one here? Okay, let's just try this, guys. Let's try this question here. Sulfuric acid, relative atomic masses are given. And then foundation guys can take a break. I'd say take a break until, let me figure this out, 7:50. Well, actually, you can stay on the live stream because we are going to do questions which are relevant to everyone, and you guys can just miss out the mole calculations. So yeah, maybe just have it on, and then whenever I'm talking about moles, just put me on mute or something. All right, we've got the answer straight away. H2SO4, so 2 lots of 1s. So 1 times 2 is 2. That's for the H2. We've got 1S, which is 32, plus 4 lots of 16s. Everyone's saying 98. Smashing it, guys. 98 for that one. Okay, time to go through moles, guys. Everyone's favorite. I'm joking. I know people don't like moles. So what do we need to know about moles? What's the definition of a mole? 1 mole is what? Can someone tell me what the definition of a mole is? Equation is mass over MI, yeah, but definition is not that. What does 1 mole have in it? Someone saying the number, yes. 6.02 times 10 to the power of 23. But how is that related to it? Here we have it here. The amount of atoms. Okay, good. 1 mole of any substance has the same number of particles as Avogadro's constant. Okay, so if you have 1 mole of anything, it doesn't matter what it is, whatever substance it is. If you have 1 mole of it, you always have the same number of particles in it. All right, which is 6.02 times 10 to the 23. A mole is just like a unit for the amount of a substance. So I could say I'm giving you 1 gram of carbon, or I could tell you I'm giving you 0.1 moles of carbon. Yeah, it's just a way of measuring the amount of a substance. And in a mole, there's always the same number of particles. Yeah, mostly it's the same number of atoms. As well as that, 1 mole of any substance always has the same mass as its relative formula mass. For example, if you had 1 mole of carbon, okay, imagine you had 1 mole of carbon, you can automatically say, I have 6.02 times 10 to the 23 atoms of carbon. Yeah, because it's 1 mole. Anything with 1 mole always has that many atoms. As well as that, I can also say I have 12 grams of carbon. So 1 mole of carbon is 12 grams because the relative formula mass of carbon is 12. If you look that up in the periodic table, you'll see it's 12. Same with water. If you have 1 mole of water, you have 6.02 times 10 to the 23 water molecules. At the same time, you can say you have exactly 18 grams of water. Why? Because that's the MR of water. You do 1 plus 1 plus 16. So those are 2 different definitions of moles. The equation for moles, guys, you need to memorize this. You don't get an equation sheet for chemistry. Moles equals mass over MR, all right? And if you want practice, guys, you've got loads of examples here. If you struggle with calculating moles, you can try them out here. Either look at the cheat sheet or go on our website, go to the moles topic, and we've got this table here. Cover them up, yeah? So cover up like all of this. Look at the question, 10 grams of water. How many moles does it have? This is what you'll do. If you're doing 10 grams of water, you'll do moles is equal to mass over MR. 10 grams of water, so that's going to be 10 grams at the top for mass, divided by the MR of water. Remember, it's 1 plus 1 plus 16. And you work that out. This is what you'll get. So practice that, guys, if you're struggling with moles. Yeah, so do the working out. Here's the working out. And then here's the final answer. Just cover it up and go through it one by one, one by one, one by one. Honestly, it comes with practice, guys. It comes with practice. You might get asked to work out mass from moles. There, you need to rearrange the equation. So we know moles is equal to mass over MR, but you also need to be able to rearrange that. If you're trying to work out mass, mass is equal to moles times MR. All right, again, we have a lot of examples here. So here we've got find the mass of 0.25 moles of water. You do moles times MR, so it'll be 0.25 moles times the MR of water. That's 1 plus 1 plus 16, which is 18. And you'll find out the mass. Okay, so show me the triangle. There we go. For practice, guys, and you've got those tables where you can practice over and over again. All right, this moles topic is practice. There's not much theory to it. It's just equations and practice questions. Now, the next stage, the harder calculations, are the ones which involve an equation, a chemical equation. All right, so we're going to try this question out here. We have 46 grams of sodium reacting with oxygen to form sodium oxide. Calculate the mass of sodium oxide formed. All right. And I'm going to write the working out on this sheet here. Let me write out this equation. Okay, so we've got you always get given the equation 6.02 times 10 to the 23. Okay, question. 4 Na plus O2 forms Na2O. That was the equation I gave you, all right? And the question says we have 46 grams of sodium and you're trying to find the mass of sodium oxide, all right? So what I tell people to do, the first thing, if you've got a mole calculation, they always give you the equation, and I tell them to basically annotate the equation. So you see here, I wrote the known and I wrote the unknown. So the first thing you need to do is identify what the known is and what the unknown is. What do you know the mass of, and what are you trying to find out? We know the mass of sodium, 46 grams. We're trying to find the mass of sodium oxide. So I would put a K here and I'll put a U here. And I'll also put 46 grams under the sodium because we know what that is, just so you don't get confused. Okay, so 46 grams here. Let me put it in a different color. That's our known. That's our unknown. And the steps that I always tell my students to go through is CREW. Find the moles of the known. So the K is for known. Then use the ratio step. I'll show you what that is in a second. And then find the unknown. So first step, find the moles of the known. So we're going to get the 46 grams and we're going to work out how many moles that is. Moles is equal to mass over MR. Mass is 46 grams. MR of sodium, if you look that up in the periodic table, someone told me earlier, is 23. So 23, 46 over 23. What's that equal to? It's equal to 2. So there are 2 moles of our known, which is sodium. So 2 moles of sodium. In this step, guys, a lot of you are going to ask, why do we not multiply by 4? You don't look at these big numbers. You don't use the 4, you don't use the imaginary 1 here, and you don't use the 2 here, okay? You only use that in the second step, the ratio step. So save that for the ratio step. Ignore the big numbers until the ratio step. So now we're on the ratio step. What we're trying to do is write a ratio of the known to the unknown. So that's sodium to sodium oxide, Na2O. So what we do is we look at the big numbers in front of them. There's a 4 here in front of Na. There's a 2 here in front of Na2O. So that's a ratio of 4 to 2. So basically a halves. So if you have 2 moles of sodium, that means you only have 1 mole of sodium oxide. Sodium oxide. Okay. Now we take that on to the final step where we're trying to work out mass. Mass is equal to, so what we're trying to do in the final step is find the mass of the unknown. We do mass is equal to moles times MR. So we're going to take the 1 mole times it by the MR that we've got of Na2O. What's the MR of Na2O, guys? What's the MR of Na2O? 23 plus 23, because there's 2 sodiums, plus 16 is 62. So we're doing 1 times 62, which is 62 grams. All right. Comes with practice, guys. After this live stream, if you want to practice more of that, we've got a lot of past exam questions on our website. Okay. Keep going through them and practicing them. Just follow these steps. Cool. Let's try some exam questions. Now, ammonia molecule here, we need to draw the covalent structure here. So how are we going to do that? Hydrogen has 1 electron in it each. Nitrogen, if you look at the group that it's in group 5. So it's got 5 electrons. 1, 2, 3, 4, 5. Hydrogen needs 1 electron in order to get a full outer shell. Okay, so that means this hydrogen here needs one of these electrons. The hydrogen at the bottom also needs one of those electrons from the nitrogen, and the one on the right also needs one of those electrons. Nitrogen, remember, has 5 electrons. How many does it need to get a full outer shell? It needs to get to 8, so it needs 3 more. Where is it going to get the 3 electrons from? It's going to get it from the crosses. 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 And what are we left with? We're left with 2 dots. They're not being shared. You put it down here. Next question. Okay, here we go. We have a calculation. The equation for the reaction between nitrogen and hydrogen to produce ammonia is this. Calculate the mass of hydrogen. So let's label our known, our unknown. Guys, what's the known and what's the unknown in this question? Let me know in the chat. Percentage yield and atom economy. You can watch that in our recording. We sent everyone a recording on the Easter boot camp. You can see we go through that. Hydrogen is our unknown. Calculate the mass of hydrogen. Our known is ammonia. They've told us the mass of ammonia. Okay, we're going to do this, and I tell all my students to do this as well. So we're going to put 25 grams for ammonia, and I'm going to put a question mark on hydrogen. That's what we're trying to find out. So this is our known, and this is our unknown. And we're going to follow those steps. Crew. So first step, find the moles of the known. We're going to do moles is equal to mass over mR. Because I've labeled it, I'm not going to get confused now. We want the mass of ammonia, which is 25 grams, over the mR of ammonia, NH3. So that's going to be 14 plus 1 plus 1 plus 1. That's 17. So 25 over 17. What's that as the answer, guys? What's the answer there? For 25 over 17. 1.47, thank you. 1.47. So we have 1.47 moles of ammonia. Now we can move that to our ratio step. What's the ratio? This is the trickiest type of ratio you can get. Remember, we want the ratio of the known to the unknown. So it's 2 to 3. It's not 3 to 2. It's 2 to 3. It's always known to the unknown. So 2 to 3 is our ratio. We have 1.47 moles here. This is when you need to do a bit of maths. How do you get to the 3 side? What do you need to do here to get the 3? If it was a 2 to 1 ratio, it'd be easy. You just need to half it. If it was a 1 to 2, it's easy. You just need to double it. But if it's 2 to 3, there we go. We got it in the, yep, people are telling me in the chat. That's good. You want to divide by 2 times by 3. That's what you need to do. So 1.47 divided by 2 times by 3. What does that give? Has anyone worked it out with a calculator? 2.205. Thank you very much. 2.205 moles. Now we have the moles of our unknown, which is hydrogen. Final step, find the unknown. We want the mass of hydrogen. Mass is equal to, we're going to rearrange this equation, moles times mR. So that's going to be 2.205 times the mR of H2. H2 is 1 plus 1. The mR of that is 1 plus 1, which is 2. So we're just going to multiply that by 2 to get, anyone got the answer here? 4.41. Well done, well done. 4.41 grams is the final answer. Okay, 4 marks for that, 4 marks. So guys, keep practicing. It comes with practice. Comes with practice. We're going to skip this one because we haven't done this topic yet. Let's go on to the next one. Describe the arrangement of carbon atoms in the nanotubes. What would you guys say for this? For 1 mark, describe the arrangement of carbon atoms. Uniform, I don't think that'll get you a mark. Cylinder, I don't think will get you a mark because it's the structure of the carbon atoms. Hexagonal will get you a mark. Hexagonal rings of carbon atoms is what will get you a mark. That's a harsh question because I know loads of students would say it's cylindrical. Hexagonal rings, because look, they're all hexagons. The atoms themselves are in hexagonal rings. I think that's a bit harsh, but that's my opinion. I'll say hexagonal rings in a cylinder. Yeah, but you actually only get the mark for hexagonal rings for this question. Nanotubes are used in electronics. One other use of nanotubes. Anyone know? Any other use of? Hollow doesn't get you the mark either. No, it's all about the hexagons. Hexagons. What else do we have? Yes, we've got nanotechnology. Nanotech. I'll tell you what you get marks for. You get marks for nanotechnology, materials, nanomaterials. You can talk about specific sporting equipment like tennis rackets. You can say drug delivery as well. Yeah, materials. Sun cream comes under materials. Yeah. Nanotube contains 2,380 carbon atoms. How many moles is that? And we've got Avogadro's constant. Ooh, let's think about this, guys. How many moles in 2,380? What do we need to do here? What do we need to do here? So you got to think about this. Remember, 1 mole, if you have 1 mole of carbon atoms, you've got 6.02 times 10 to the 23 atoms, right? That's the definition. We want how many moles, so I'm going to put a question mark, for 2,380 atoms. So we're basically trying to go from here to here. How do you get from 6.02 times 10 to the 23 to 1? You divide. You divide by 6.02 times 10 to the 23, right? That's how you get to 1. We're going to do the same here. We're going to divide by 6.02 times 10 to the 23. So the working out we need is 2,380 divided by 6.02 times 10 to the 23. Anyone got the answer there? And there we go. Someone's got it. 3.95. 3.95 times 10 to the minus 21 moles. Well done, guys. Explain why carbon nanotubes can conduct electricity. Let's see if you guys remember this. What do we say here? Carbon nanotubes. Similar to graphite because they're hexagonal rings, right? But the hexagonal rings are in a tube. Have delocalized electrons. Yes. It's a 3 markers saying that it's not enough. Why does it have delocalized electrons? Because each carbon atom is bonded to 3 other carbon atoms. So there's a free delocalized electron. So each carbon atom is bonded to 3 other carbon atoms. Yes. So there is 1 delocalized electron. Per atom. And then we can say it can carry a charge, not energy this time, a charge through its structure. We haven't done any required practicals yet, guys. That's because the first 3 topics in chemistry doesn't have a required practical. They all come in topic 4 and 5. We've got a few coming up in the next part. What type of reaction is this? We haven't done this yet. Anyone know the answer here? You don't understand the difference between electrostatic and intermolecular. Still, electrostatic is between positive charge, negative charge. Intermolecular is between molecules, intermolecular. Okay, that's the difference. If you have something positive and something negative, that's electrostatic. If it's between molecules, it's intermolecular. Displacement, no, it's neutralization. Neutralization. You've got an alkali here, and you've got an acid here. I know we haven't done neutralization yet. That's later on. That's in topic 4. But yeah, this is neutralization. Neutralization. We've done this one already. Calculate the percentage by mass of oxygen in lithium sulfate. You could get asked a question like this, the percentage by mass. So how much oxygen is there in Li2SO4? We just need to use the MRs and the ARs here. There's 4 lots of oxygen in here, but we need to work out what that is as an MR. So what we want is basically find the MR of this, of 4 oxygens, then find the MR of the whole thing and divide them. So that green bit, we know oxygen is 16, but there's 4 of them. So it's going to be 16 times by 4 divided by the red bit, which is everything, which they've given to us nicely. So you just do 16 times by 4 divided by 110 is the percentage we're trying to calculate. So we need to multiply that all by 100. Anyone got the answer here? Not 64, it is 58%. Someone said 58.18. If you said that, you'd only get 3 out of 4 marks because this. Please don't fall into that trap, guys. Tomorrow, if they say give your answer to 2 significant figures, remember to do that. So 58% to get that. A solution of lithium sulfate contains 0.3 grams of lithium sulfate in 25 centimeters cubed. Calculate the concentration. Guys, equation for concentration. Can you guys tell me in the chat what's the equation of concentration? Because we haven't gone through that. What is the equation for concentration? Okay, so there's 2 equations. Yeah, concentration is equal to mass over volume. If you're combined signs, that's all you need to know. Okay, mass is in grams, volume is in dm cubed. I'm going to tell you all about dm cubed in a second. The other one, if you're triple, you also need to know concentration is equal to moles over volume. Moles is measured in mol, and volume is measured in dm cubed. If you use that equation on the left, then concentration is measured in grams per dm cubed. If you're using that equation on the right, it's measured in moles per dm cubed. So there's 2 ways you can measure concentration. How do you go from centimeters cubed to dm cubed? Because the question's asking us to work out in dm cubed. How do you go from centimeters cubed to dm cubed? This is a very important conversion you need to know, especially if you're triple science, guys. Centimeters cubed to dm cubed, divide by 1,000. Well done. Dm cubed back to centimeters cubed, you times by 1,000. The amount of students I see who forget to do this is insane. So we want to convert 25 centimeters cubed into dm cubed. So we're going to do 25 over 1,000. 25 over 1,000. And then that gives you 0.025 dm cubed. Now we can put it into that equation on the left to work out the concentration. So concentration is equal to 0.3 over 0.025. What do we have as the answer here? 12. Well done, guys. 12 grams per dm cubed. Good stuff. Good stuff. Wow, look at that. Perfect on time. 7:40, guys. Time for a break. Time for a break. All right. The serious stuff's coming up with electrolysis coming up in the next session. So, break time, guys. 10-minute break. And we're going to jump to topic 4. You guys are doing so well. Keep it up. Keep it up. See you guys in 10. See you guys in 10. So I'll see you at 7:50. 7:50. Welcome back, everybody. We're on topic 4 now. How is everyone doing? Nearly there, nearly there. Topics. We're going to go through reactivity series. We're going to go through 2 required practicals today. In the next session, we're going to go through electrolysis and the making salts practical. Yes, good to hear, good to hear. I know chemistry is a tough one. In my opinion, chemistry paper 1 is the hardest science paper. I don't know if loads of people agree there, but I think it's hard because of electrolysis and moles. I think it's the hardest one. So I'm with you guys on that. Right, so let's go through the reactivity series first. You had lunch, you had dinner in 5 minutes. That's a quick dinner. Okay, so reactivity series. Here we go. This is the reactivity series. Most reactive elements here, least reactive elements here. Okay, potassium is the most reactive one in the ones that you need to know. Okay, so what I've done here is I've created the reactivity series for the ones in the spec. Underneath here, you might have seen silver and gold. That's fine as well. But basically, yeah, it goes potassium, sodium, lithium, calcium. And I've got some non-metals here, carbon and hydrogen. Carbon is used for extracting a metal, and hydrogen is used for electrolysis. You'll see why in a second. So what do you need to know about this? You need to know what happens. How can you tell something is more reactive? So how can you tell one element is more reactive than another element? And you can do that by reacting them. So, for reacting them with water. Imagine getting all of these elements that I just listed out and reacting them with water. What would you expect? You would expect a more violent reaction with the ones that are more reactive, and not much bubbling, not much effervescence, with the ones which are less reactive. Okay, so they might ask you things like that. So if there's a more violent reaction, it means it's more reactive. You can also do a reaction with dilute acid as well. And again, it's the same thing. The more violent the reaction is, the more reactive the element is. Quite simple. Okay, and I've got a few equations for that as well. So that's one of the things that I wanted to go through very quick because it comes up quite a lot. Next thing I wanted to go through was the pH scale and neutralization. We mentioned neutralization already. So neutralization is a reaction where you have an acid and an alkali reacting together. What do acid solutions release, guys? So if you add an acid to a solution, what does it do? What does it release? Let me know in the chat. H plus ions. Thank you very much. H plus ions. What about an alkali? What does an alkali release in solution? An alkali releases OH minus. Yes, well done, guys. So when you have neutralization, you've got an acid reacting with an alkali. Let me write this in the workbook. Acid reacting with an alkali. And that always forms two things. What are those two things that get formed, guys? Underneath this, I'm going to write the ionic equation. Acids release H plus, and you guys just told me alkalis release OH minus. What does it always form? It forms salt and water. Salt and water. Well done, well done, well done. Okay, for the ionic equation, what happens when you get the H plus ions and add them to OH minus ions? What is that going to form? It's always the same here. It's going to form H2O, okay? So if they ask for the ionic equation for this, this is all you write. And then what we have at the top is the general equation, which could change based on what the acid is and what the alkali is. All right. How can you measure pH? Well, you can use an indicator such as a universal indicator, and universal indicator will change color when you put it in the solution. These are the colors that you've got. So if it's red, very acidic. If it's orange, it's slightly acidic. If it's green, it's neutral. If it's blue, it's slightly alkali. And if it's purple, it's very, very alkali. So it always goes from 0 to 14. You need to know these numbers as well. Now, the problem, what's the problem with using universal indicator? Why is it not the best way to find the pH of a solution? Why is it not the best way? What would you say if you got asked that? Why is using universal indicator the best way to find it out? It's not accurate because different eyes need glasses. It's subjective. Yes, I like that word, subjective. Different people see colors differently. Okay, so like this, for example, some people will say it's orange, some people will say it's red. It depends. It's a bit of both, isn't it? So it depends on the person who's analyzing it. And if it's purple, how purple is it? You need to figure out, is it a 12, is it 13, or is it 14? It's very subjective. It's all based on the person that's analyzing it. What's a much more accurate way is to use something called a pH probe, which is literally a probe, like a stick you put into the solution, and it gives you a number. Not subjective, it's objective. It tells you the exact pH. So say like 7.05 or whatever. Okay, and then here we have the two equations that I just wrote down as well. Okay, so after that, what this links to is the first required practical that we're going through, which is to make salts. Memory trick here for making salts. How do you make a salt, guys? Who knows the memory trick? I think I posted it yesterday. Required practical. If you get a 6 marker asking you to create a salt, what would you use? HEFEC. Yes. Okay, so the steps are H, E, F, E, C for this one. So what do we want to do first, guys? What's the H for? So we're trying to make a salt. Okay, so we need an acid, and we need a base, right? So the base is usually, I'll show you guys here on the cheat sheet, it's usually an oxide or a carbonate. Okay, so we have an insoluble base reacting together with an acid. Okay, so in the question, they might say, the student is trying to create lithium chloride, yeah, some salt. We know it's a salt because it's ionic, it's a metal and a non-metal. And they'll ask you, prepare an experiment to make salts of lithium chloride. So you need to decide what acid to use and what base to use, what alkali to use. The acid you need to use, it all is based on the second part of the name. So if it's a chloride, we got it here. If it's a chloride that you're trying to create, you need hydrochloric acid. If it's a nitrate you're trying to make, you need nitric acid. And if it's a sulfate, you need sulfuric acid. So if it's lithium chloride, we'll need hydrochloric acid. So we get the chloride from there. Where do we get the lithium from? We need an oxide or a carbonate. So you need either a lithium oxide or lithium carbonate. Either one of those, it's fine. Okay, so that first step in HEFEC is heat up your acid, hydrochloric acid. Okay, so we're going to do this example for lithium chloride. And we're going to apply it to that. So heat. And we have to say the correct acid here, hydrochloric acid, but it could change based on what the question's asking you. in a beaker. Then what you do after that, what's the second E for? So H is for heat. What's the E for, guys? What's the E for? Not evaporate. We don't evaporate yet. Excess. Excess. Let me put it in a different color here. Excess. You have to add that solid in excess. So we've added the hydrochloric acid into a beaker. We've warmed it up. Now we're adding our lithium. So if you remember, it's lithium oxide or carbonate. Either one of those will get you the mark. So add lithium oxide. And you say in excess. In excess. Excess just means you have more of it than is needed for the reaction. So you keep adding it, keep adding it, keep adding it until it stops like dissolving, stops reacting. Because imagine you have the acid and you put the lithium oxide in, it's every time you add it in, it's going to disappear, right? It's going to react. But if eventually, if you add enough, all of the acid's going to get used up and you're going to have excess lithium oxide and it's just going to sink to the bottom and it's not going to react. At that point, you know you have used up all your acid. Okay? What do we do next now? So we have our acid fully reacted and now we have extra lithium oxide. What do we need to do? Filter. Yes, we want to get rid of all that excess lithium oxide. That's not going to make us salt. That's just extra, which hasn't reacted. So filter out the solid. We'll say the excess solid. Lithium oxide. We don't want that anymore. What you're left with is the liquid. That is what you want, because in that liquid now, you have the salt you're trying to make. You have lithium chloride, but you have it in an aqueous form. It's dissolved in water. We want crystal salt. So what do we need to do next? What's the E for, guys? What's the E for? Yes, I would memorize the reactivity series. Yes. Evaporate. Evaporate. Yeah, we want to get rid of a lot of that water. So you want to evaporate off the water to make the solution more concentrated. So you want to heat in a water bath to evaporate off water. And then you basically start seeing crystals of the salt that you're trying to make. And it's nearly there. What do we need to do at the very last bit then? Last bit. So it does crystallize. It crystallizes. Yeah, we want to cool and dry. So we want to take out those crystals. We want to leave them to cool and to dry. So you can remove the crystals by filtration again if you want. So remove the crystals, cool, and dry them. And then you're done. Got people spamming the chat. If there's something I haven't covered, guys, remember you can watch the recordings. Yeah. So if it's not in the list for today, I won't have time to go through it today, but you can watch the recordings. That's what it's there for. The bootcamp recording got sent to everyone there. Okay. So that is the making salt practical. We got a question on that as well in the workbook. Now, we've done reactivity series, pH and neutralization, making salts. Let's go through the big one. We've got electrolysis, which is the next required practical. What do we need to know about electrolysis? So electrolysis, electro means electricity. Lysis means split. So what you're doing is you're basically splitting an ionic compound using electricity. Remember, ionic compounds are a mixture, not a mixture, sorry, is a combination of a non-metal and a metal. So something like sodium chloride, potassium fluoride, all of those are examples of ionic compounds. And what you're trying to do is you're trying to break it up. So if you've got lithium chloride, you want to break it up into its ions. So like lithium ions, chloride ions. It's a separation technique, but it's not one of the ones that you learn. So it's not like filtration or distillation or evaporation, any of those, because this is a chemical separation techniques. Those ones can only separate mixtures. We're trying to separate a compound here, all right? So we have to use electricity because it's difficult to separate a compound. They've got all those strong ionic bonds. We want to break those, so we use electricity. The setup here is like this. What you have in this setup is two electrodes. Two electrodes. These electrodes are made out of graphite. They're made out of graphite because graphite is inert. Inert means it's unreactive. You hook them up to a power supply, so like a battery, and then you put them into this liquid. What's the name of this liquid, guys? What do we call this liquid? Panic and oil rig. Nice. I like it. That's called the electrolyte. Yes. Electrolyte. The electrolyte is whatever it is that you're trying to split up. Okay, so it would be the lithium chloride. It would be always an ionic compound. Not always, sorry, not always an ionic compound. Mostly it's an ionic compound. Yeah, but it's always the thing that you're trying to split up. And those electrodes that I talked to you about, there's always two. There's the positive electrode and the negative electrode, okay? And like everyone said in the chat, you can use panic to figure out which one is positive and which one is negative. So positive is the anode and negative is the cathode. So that's our setup. Now, in our setup, we have loads of ions. Those ions need to be free to move. Electrolyte is the ionic compound. But remember, ionic compounds are normally solid, right? But what's the problem with a solid? I told you guys at the start of the stream, solid ionic compounds cannot conduct electricity. What do we need to do to make an ionic compound conduct electricity, guys? Let me know in the chat. What do you need to do in order to make ionic compound conduct electricity? You need to either melt it, good, or dissolve it in water, because that makes the ions free to move. Now that they're free to move, they can conduct electricity. That's why the electrolyte has to always be molten or aqueous. All right? So we pass electricity through it. When it's molten and aqueous, we have all the ions floating around. So let's say, for example, we're using sodium chloride, NaCl. Let me draw this here so I can draw it neatly, because I know this is the one everyone's struggling with. So 2 electrodes. We have our battery source and we have our electrolyte. Okay, so we're doing molten sodium chloride. What are the ions in molten sodium chloride? Let me know in the chat, guys. What's the ions in molten sodium chloride? What do we have in here? We have 2 types of ions. We have Cl minus, yep, Cl minus ions, so chloride ions, and sodium ions, Na plus ions. Okay, so in our solution here, we have floating around everywhere Na plus ions and chloride ions. They're just floating around in our liquid, in our electrolyte. Okay, we have our anode, which is positively charged, and we have our cathode, which is negatively charged. what's going to happen, guys? What's going to happen? Positive charge is going to go to the negative cathode because they're oppositely charged, so they get attracted. Negative one occurs here, and it goes to the anode. It goes to the positive electrode. Two separate things happen at the anode and at the cathode. So eventually, this positive ion is going to reach your anode, and a reaction is going to happen. What reaction is going to happen? So I tell people to use ORAC. So oxidation always occurs at the anode. Reduction always occurs at the cathode. What does each of these mean? Well, you can use oil rig here. Oxidation is the loss of electrons. So it's when electrons get lost, gets removed. Reduction is the gain of electrons. So at the anode, so that's this side here, we have our sodium ion. Sorry, our cathode. Sorry, my bad. This is the cathode. So at our cathode, we've got the sodium ion going to our cathode. So it's attracted to the cathode. And when it gets there, it discharges. These ions always discharge at the end. That means they either gain electrons or lose electrons. It depends on whether it's the cathode or the anode. So because this is the cathode, what's going to happen? Reduction is going to happen. What's reduction? Is the gain of electrons, right? So Na plus is going to gain electrons. Na plus gains electrons to form, the end goal is always an atom. Na without a charge. So Na plus goes to Na. On the anode side, it's the opposite that happens. So on the anode side, it's not going to be the sodium that's attracted to it. It's going to be the chloride. So Cl minus is attracted to the anode. Again, why? Because they're attracted due to opposite charges. Positive and negative get attracted to each other. This time, chlorine is negative. It's happening at the anode. What happens at the anode? Oxidation occurs at the anode. Oxidation is the loss of electrons. So at the anode, Cl minus loses electrons to form Cl. But chlorine is diatomic, as we learned already, so it forms Cl2. Okay, so that's molten sodium chloride. Now, what would we observe here, guys? Tell me what you think you'd observe here. What's the observations that we'll see when we electrolyze this? Let me know in the chat. It's all to do with what gets formed. We've got sodium here, and we've got chlorine here. Bubbles. Yes, we're only going to see bubbles on one side. Which side is going to see bubbles, guys? Which side? Is it the anode or the cathode that's going to see bubbles? It's going to be anode or the cathode. Anode. Anode is going to see bubbles. Why? Because it's forming chlorine. Chlorine's a gas. You're going to basically see bubbles on this side. What are we going to see on the other side? What are we going to see on the cathode then? You're going to see the metal. You're going to see sodium metal. But it's not going to coat the electrode here, because remember, all of this is molten. This is molten sodium chloride. So it's very, very hot. What's going to happen is that sodium is basically whatever's getting formed at the cathode is going to trickle to the bottom as a liquid. And you're going to get sodium being formed here. So molten sodium's formed. So look out for that. It depends on what it is. It happens in the electrolysis of aluminium oxide. Aluminium is found at the bottom as molten aluminium because it's so hot. Okay, so this is all for molten. For molten, it's more straightforward than an aqueous sodium chloride. Molten sodium chloride forms the elements which are in the name. So molten sodium chloride will always form sodium and chlorine. Molten lithium oxide will form lithium and oxygen. Molten calcium sulfide will form calcium and sulfur. You can always figure out what it's going to form by its name if it's molten. If it's aqueous or if it's in solution, you can't do that. That's what makes it a bit more confusing. So when you see electrolysis tomorrow and it tells you the compound, see whether it says, first of all, is it molten or is it in solution? Is it aqueous? That will tell you, that will give you a bit of information on what you need to do. Because let me show you what happens if it is aqueous. Let me do it on a new page. Can anyone tell me in the chat, what happens if it's aqueous? What do we need to consider here if it's aqueous? Why is it a bit different if it's in solution? So I'm going to put an aqueous sodium chloride. H plus and OH minus. There we go. We're getting it, guys. Okay, so sodium chloride molten, we said the ions were Na plus and Cl minus, right? It is the same for aqueous sodium chloride, but this time we have extra ions. That's what makes it different. What other ions do we have, guys? We have Na plus, Cl minus floating around in our solution. But because it's aqueous, it means there's water in it. And water breaks down, let me put it up here. Water breaks down into H plus and OH minus ions. So it breaks down into those ions. That means we don't just have 2 ions. We have 4 ions to deal with here. We have H plus, OH minus ions, Na plus and Cl minus ions. This is what makes it different. This is what makes it complicated. So let's do the same thing again. We're going to put our anode on the left. We're going to put our cathode on the right. And we're going to put all of those ions in the middle. So we had Na plus floating around, H plus floating around, Cl minus floating around, and OH minus ions floating around. Now, what makes this slightly complicated is because only one positive one can go to the cathode, only one negative one can go to the anode. You need to be able to figure out which one goes to the anode and gets discharged and which one goes to the cathode to get discharged. How do you decide? How do you decide? Is it the sodium or is it the hydrogen that gets discharged at the cathode, guys? Let me see if you guys have got it already. Someone said more reactive. No, it's the less reactive one. So this is why the reactivity series is so important. It's the less reactive one that goes. So memory trick here, guys, memory trick. If you're dealing with an aqueous solution, I tell people to use Hauk to figure out what gets formed at the anode and what gets formed at the cathode. Remember, this is only for aqueous solutions or aqueous electrolytes. So at the anode, it is always the halogen that gets produced. If there's no halogen, it's the OH minus that gets produced. because remember, you're always going to get OH minus from the water. At the cathode, it's the less reactive element that gets produced. Less reactive element. Okay, so HALC. So question. Out of Na plus and H plus, this is the cathode we were talking about, which one is less reactive? Which one's going to go, Na plus or H plus? Na plus or H plus? Which one is going to go to the cathode and get discharged? It's going to be H plus. Yes, well done, guys. Because in our reactivity series, you'll see that H plus is less reactive than sodium. Sodium is very reactive. What's going to go to the anode? Is it going to be Cl minus or OH minus? Cl minus or OH minus? Cl minus is the one, because if a halogen is present, remember halogen is group 7, that means the halogen will go. We do have a halogen present. We've got chlorine, so that is going to go there. So what we will get on the anode side is we're going to get chlorine produced, so chlorine bubbles. And on the other side, we're going to get hydrogen bubbles. We're not going to get sodium this time. Hydrogen gas produced. All right. So just to keep this, guys, to keep this in your head, guys, I want to try and exercise with you guys. I'm going to give you a list of loads of different ones, and I want you guys to tell me what's at the anode and at the cathode. I have this on our website. If you want to practice what I just said, we're going to use HALC. Halogen at the anode, less reactive at the cathode. For sodium chloride, we said is hydrogen and chlorine that's produced. Next one is copper sulfate. If we're doing copper sulfate, what's produced? Is it copper, hydrogen, oxygen, or something else? So for this one, for copper sulfate, it's going to be copper, because for the cathode is the less reactive. And when you compare copper and hydrogen, so let me write this down, copper sulfate, the ions you're going to get here are Cu2 plus. You're going to get H plus from the water. You've got SO42 minus, and you've got OH minus. So out of this, which one is less reactive? It's the copper. So you're going to get copper formed. What about at the anode, guys? What's going to get formed at the anode? OH minus, because remember the rule is halogens get formed at the anode. If there are no halogens, then it is OH minus that goes. There's no halogens here. Sulfur is not a halogen. So you see here, you get oxygen being formed because the OH minus is the one that gets produced. All right, let's try another one. Last one. Sodium hydroxide, guys. What gets produced at the cathode? Sodium hydroxide. You finally get it. Nice. That's what I like to hear. So keep practicing this, guys. Go on our website, go onto this table and go through them and see if you get it. Hydrogen here, yes. Is it Na plus? Is it H plus? It's going to be H plus because H plus is less reactive. On the other side, we only have OH minus. We have no other option. We have nothing else. It has to be OH minus. So what you're going to get formed is hydrogen gas and oxygen gas. Okay? And you can just keep doing that to try and figure it out. All right. That's good to hear. That's good to hear. How are we doing for time? 8:25. Okay, so let's try some questions. Let's try some questions. This question is, we've got 6 mark here. Question is about making soluble salt. Plan a method to make pure dry crystals of zinc chloride from zinc carbonate and a dilute acid. What acid? First of all, remember, you have to decide what acid's being produced. What acid are we going to get from here? We're going to use HEFEC. Yes, we are. What acid are we going to use here, guys? You're hungry, you can eat. You can eat while watching. Hydrochloric acid, yes, because it's a chloride. If it was a sulfate, then it'll be sulfuric. If it was a nitrate, it would be nitric. So use zinc carbonate, because it says that in the question, plus hydrochloric acid. And we're going to use HEFEC here. Imagine something like this comes up tomorrow. How happy would you guys be? Fingers crossed. So heat the hydrochloric acid. All right. Then for excess, add zinc carbonate to the hydrochloric acid until it is in excess. Next, we've got the F for filter. So you filter to remove the excess zinc carbonate. And then we've got evaporate. So you want to evaporate the water. So you heat the filtrate, the liquid, until, we'll say using a water bath, until crystals form, and then cool and dry. So leave the crystals to cool and dry. Pat them dry. All right, 6 marker. There we go. Fingers crossed this comes up and you will get 6 marks if you're at this live. Next up, name 2 other substances that can each be reacted with a dilute acid to make zinc chloride, except for zinc carbonate. What else can we create, guys? What else can we use to make zinc chloride? You could use pure zinc. Yes. You could use zinc oxide as well. And you can also use zinc hydroxide. Yes, any of those would work. I'm just going to put zinc and zinc oxide. You can't say carbonate because it's already mentioned in the question. Electrolysis question here. Remember, first thing I want you guys to do when you get an electrolysis question, figure out, is it molten or is it aqueous? What is this? It says solution. Is it molten or aqueous, guys? It says solution. It is aqueous, yes. So you need to remember now, this is where we need to use that Hauck method, right? Hauck method. So in here, just before we start the question, it's copper bromide solution. We're going to have copper ions. Let me get a thinner pen. We're going to get copper ions. We're going to get bromide ions, Br minus ions, but we'll also get H plus ions and OH minus ions, okay? So which particles carry the electric charge through the metal wire? What do you guys think the answer for that is? What carries the charge through the metal? Here, electrons. Yes, through the metal, it's electrons because of the delocalized electrons. Through the solution, it's the ions. So electrons is the answer here. Oh, they've told us the ions. They've been nice and they've given us the ions here. Two of these ions are formed when a water molecule breaks down. The simple equation is this. Complete the word equation here. Easy. We call H plus ions hydrogen ions. What do we call OH minus ions? Hydrogen ion and hydroxide ion. Yes. Hydroxide ion. Copper ions and bromide ions carry the electrical charge through the solution, like I told you guys earlier. Formula Cu2 plus and Br minus. What is the formula of copper bromide? Okay, so this is a technique, guys, to work out the formula of something. It's called the swap and drop method. So if you've got something ionic and you want to work out its formula, write it up like this. Br minus is -1. And what you do is you get the two numbers and you swap them and you drop them to the bottom. Swap and drop. So the copper is going to get the 1 from the bromine, and the bromine is going to get the 2 from the copper. So Cu1Br2. So it's called CuBr2. We never write the ones. CuBr2. You can do that for any ionic compound if you want to work out the formula for it. And no, it's not because it's diatomic, guys. Someone said it's because it's diatomic. No, it's only diatomic when it's on its own. This is just a coincidence. It could be single Br, like NaBr does not have a 2 in it. It's only diatomic when it's on its own. As an element, it's Br2. Next one, explain why copper ions move to the negative electrode for 2 marks, guys. What can we say here? Why do they move to the negative electrode? We don't need to say about what happens when it reaches. We just need to say what happens or why it moves. What can we say here? Don't need to say less reactive. No, you just need to say attraction. It's attracted to it. Yeah. This is positive. So copper ions are positive. And they are attracted to the negative cathodes. Next one, complete the sentence. At the negative electrode, copper metal is produced when the copper ions are. What happens to the copper ions, guys? So you're going from Cu2 plus to Cu. Cu2 plus to Cu. Discharged. They're discharged. Discharge just means they're losing their charge, right? Because they're always going from an ion. You always go from an ion to an atom. That's called discharging. What happens to the mass of the negative electrode during electrolysis? Let's see. Negative electrode here. What can we say? What do you guys think? Someone says no change. No, it is going to increase because the copper sticks to electrode. Yes, GCSE account. I think that's your name. Yeah, you got it. So what's happening is, okay, let's figure out what gets formed here. Guys, out of the positive ones, which one's going to go to the negative electrode? Is it going to be Cu2 plus or is it H plus? Remember Hauk. Which one's going to go? H, okay? Is it H? No, it's not H. It's not H. Look at the reactivity series. Underneath hydrogen, you've got one metal. It's copper. Copper is less reactive. Copper is the one that's going to go. Copper is going to get formed. What about on the other side? Is it going to be bromine or is it going to be OH minus that goes? Hauk is for aqueous only. Yes, this is an aqueous question. Br minus, yes, because it is a halogen. So on this side, you're going to get copper being formed. So what are we going to observe? liquid. So you're going to probably get liquid being added here. On this, we're getting solid copper being formed. So what that's going to do is it's going to basically get formed on the outside of the electrode. The electrode is going to get lined with copper and it's going to get bigger and bigger and bigger. So this copper electrode is going to get heavier because it's a solid being attached on. The answer here is the mass is going to increase. What is produced at the positive electrode when copper bromide solution is electrolyzed? You guys can tell me now. You've told me already. What's the answer here? Cu2 plus, Br minus, H plus, OH minus. Sorry if it's blurry. Hopefully it'll get better in a bit. It's going to be bromine. Okay, on that note, guys, flagging. We'll take a pause before the last session. We'll be back in about 10 minutes. 10 minutes. So let's come back at 8:45 for the final thing. Hopefully this lag would have stopped and we can finish off, guys. Got one more topic to do. All right, I'll see you guys in 10. See you at 8:45. Last 45 minutes, guys. You guys are smashing it. Hey guys, final session. How is this? How's the connection, guys? Is it lagging still? Said my connection's a bit unstable, but how is it looking? We've got about 45 minutes left, guys. Better? Okay, fingers crossed it stays good for the last 45 minutes. You guys are smashing it. Remember, I think this is the hardest science paper there is. So just stick with me for 45 more minutes. We're going to go through one more required practical and also talking about energy in reactions, and then we can go back to those electron questions if you guys want. Let's see how we do for time. It's not much for topic 5. It's the shortest one. How do you remember the reactivity series, guys? What's the mnemonic you guys use for the reactivity series? Why don't you type in the chat? Something about lazy zebras, isn't it? What is that one? Type in the chat. There's loads there. Okay, so fine. We got exothermic and endothermic reactions. I posted a video on this earlier, guys. What's the difference between an exothermic and an endothermic reaction? How do you remember them? Sorry for the lag, guys. Hopefully it gets better in a bit. Endo, En is for enter because heat enters it. Heat is absorbed. Thermal energy is absorbed. The DO can remind you of down because temperature always goes down in an endothermic reaction. Okay. Exothermic, you got the EX here for exit. Because thermal energy, heat, leaves the system. It's produced, not produced, don't say produced, gets released. Don't say produced for energy ever. It never gets made. Thermal energy is released to the surroundings. And you can tell a reaction is exothermic because the temperature goes up. It's the opposite. So use the DO in endo to remind you that it goes down, and that makes the other one the opposite. It goes up. It goes up. Okay, so what else do we need to know here? Examples. These are the ones which are in the spec. Okay, examples of exothermic reactions. Neutralization reactions, combustion reactions. So when you burn a fuel, that's a combustion reaction, and loads of oxidation reactions. Practical uses, hand warmers, self-heating hands. These self-heating cans, sorry. They come up in the mark scheme all the time, okay? Then for endothermic reactions, we've got thermal decomposition. That's when you heat something up and it breaks down. And this is a really specific one that was in the spec. I've never seen it come up. I don't know if you guys have. Reaction between citric acid and sodium hydrogen carbonate. It's very random, but yeah, it's there. I don't think I've seen it in an exam before. Practical use, sports injury packs. So there's ice packs which don't actually use ice. They have like a bag which you basically break and then it gets cold. That's a use of endothermic reactions. All right. Just before we go through the required practical, let me go through the two reaction profiles. So reaction profiles are basically diagrams that show you how energy changes with the reaction. So as the reaction progresses, how the energy changes. So for an exothermic reaction, the reactants start off high and then the products are lower. These graphs always have a hump in it. So it always goes up and then it drops down. But for exothermic, the rise is small and then the drop is very big. So you always end up at a lower level. Activation energy, this is the minimum amount of energy needed for particles to collide for the reaction to occur. That's always the height of this hump from the reactants. And then the overall energy change is the difference between the reactants and the products. So for exothermic reactions, they always go down. For endothermic reactions, they always go up. So you can see here, the activation energy is much bigger and the energy change is still the difference between reactants and products. All right. Right, let's go through this final thing, required practical, and then we've got a lot of time to try some questions out after that. So this required practical, I do have a memory trick for this as well, guys. Investigating energy changes. So seeing how much energy changes within a reaction. So in a reaction, you always have an energy change. Energy is either taken in or given out. So it's either exothermic or it's endothermic. We can tell how much energy is given out or taken in by looking at the temperature change. It's all about looking at the temperature change. The larger the temperature change, the bigger the temperature change, the more energy is given out or taken in. So what we do in this practical is we get the mass of something and we get an acid. We react them together because that's an exothermic reaction, and we see how much the temperature rises by. And by looking at that, you can tell how much energy is released. The bigger the temperature rises, the bigger the energy change. So you can start investigating like different types of metals, for example, or different masses of metals, or different concentrations of acids. How much energy is being released every time you do that? Now, what's the memory trick here, guys? Who knows? I posted a video on this today, actually. Today, I think. Vichar, yes, that's the one. That's the one. Okay, so what you want to do here, so remember, it's an acid reacting with some sort of solid, yeah? So what you want first is you need the fixed volume of acid. You need a certain volume. You need to be able to measure that volume. So that V there is to mention measuring the volume. So add a certain volume of acid to a beaker, and we're going to mention that we're going to measure using a measuring cylinder. I'm going to say measure using a measuring. I, what's the I for, guys? This is practical and it's all to do with temperature change. What do you think what do we need to mention here? Insulation, yes. Because this is all to do with temperature and we're measuring the change in temperature, we want to keep all that heat energy within the reaction. We don't want it to escape to the surroundings because that's going to make your reaction less accurate. You want to contain it all. So you need an insulator here. What's an insulator that you can use? What's the insulation that we can use here to make this reaction more valid? Sorry if it's blurry. Let me zoom in, guys. Hopefully you can hear me. Can you hear me okay at least? I'll talk through it. Polystyrene cup, yes. So you can use a polystyrene cup. You can hear me? Okay, that's good. So polystyrene cup and a lid. You want a polystyrene cup and lid. Mention that. Then we've got the T. What do you guys think the T is for? Temperature. Yes, we've got temperature. So what you want to do next is you want to measure the initial temperature of the acid. How are we going to measure the initial temperature? Measure the initial temperature using, thank you guys, using a thermometer. Okay, S. S, this is something to make it more accurate. What's the S for, guys? The S is for stir. Yes, it is. So what you want to do is you want to stir the mixture. So you basically have a solid within the acid, and you want to make sure all of it reacts. So you want to stir it to make it as accurate as possible. So stir the mixture. Remember to mention that. H, what's the H for, guys? What do you guys think the H is for? This is something people always forget to mention. Highest temperature, yeah. So people say find that temperature change, but you need to mention, you need to note down the highest temperature, because what happens is you start off at a low temperature, it rises, and then once the reaction's finished, it starts to cool down, because that's what naturally happens. What you want to do is note down the temperature like every 5 seconds, and then see where the highest temperature is and note that down. So H is for highest. So note down the highest temperature. What's the A for then, guys? Finally, the A. Why do you add the solid? Because you want the reaction to occur. It's the reaction that you're measuring, right? You need to add the solid in order for the reaction to happen. Yes, it's basically repeating, yeah? Again, so you repeat this whole thing, but this time you repeat it by changing one of the variables. So if you're investigating the mass of the solid, first time round, you add 10 grams of the solid, then you repeat the whole thing again, but using 20 grams, then 30 grams. If you're investigating the type of metal, the first one you use iron, then you repeat again using copper, then zinc, and so on. So that's what the last one is there for. Repeat and change. No, let's repeat. Yeah, and change variables. Change a variable. Change one variable. You don't want to change more than one. You want to keep everything else constant. And then you've got all of them, all of the steps covered then. All right. Cool. Let's go through some questions. Start off with questions on this practical now. The last bit here, guys, final bit. So someone's doing this experiment. So a student investigated the temperature change when different masses, so they're investigating different masses of zinc, were added to copper sulfate solution. Let's look at their method. Let's see if we can improve this. They poured the solution into a polystyrene cup, so that's good. They don't have a lid, but okay, fair enough. But at least they're using insulation. Measure the starting temperature, so initial temperature. So they've done the V and they've done the I, so volume of copper sulfate, and they've used insulation. Measure the temperature, starting temperature done. Then they added the mass, the zinc. Then they stirred, and then they measured the highest temperature, and then they repeated. So they've done all the steps here. All right. Now, the student varied the mass. What type of variable is that? If it's varied, guys, if it's varied. Independent variable, yes. Control is the one that we keep the same. Dependent is the one we measure, and independent is the one we change. Yep. Next. Here, zinc reacts with copper sulfate to produce salt and copper. What salt is produced? You've got zinc and copper sulfate. What's the salt that's produced, guys? What do you guys think? Yeah. Yeah, that's right. That's all you need to know for the variables. Things. Titrations, go and watch the recording. We sent everyone a recording. I go through titrations in the Easter Bootcamp one. Yeah. It's going to be zinc sulfate. Yeah, what's happening here? What type of reaction is this, guys? Look at that. The zinc is taking the place of the copper. What type of reaction is that? Displacement. Yes, it is. It's displacement. The temperature of the solution increases when zinc reacts with copper sulfate solution. Give 2 other observations that can be made when zinc reacts with copper sulfate. Do you guys know what copper sulfate looks like, by the way? This is like one you should probably know. It doesn't say so in the spec, but they do expect you to know what copper sulfate looks like for some reason. Does anyone know what it looks like? Yeah, it's that blue one. It's the blue liquid. So remember that copper sulfate is a blue liquid. It's a blue solution. Blue solution. All right. Most other solutions aren't blue. Most of the ones you come across are colorless. So what do we think happens when zinc reacts with it? So it's going from copper sulfate. You're adding zinc and it turns to zinc sulfate. So what's going to happen is color change. Yes, color change. That blue solution turns into a colorless solution. So solution turns colorless. What else can we say, do we think? Let's look at that reaction again. Look at what gets produced. Copper. What does copper look like? What can we say about copper? Not bubbling. Why can we not say bubbling here, guys? Why would bubbling not get you a mark? Because there's no gas formed. Yeah, no gas. This is a solution. This is a solid. There is an orangey solid produced. Copper is like an orangey solid. So you can say orange solid produced. Okay, next question. Figure 6 shows the highest temperature reached. Okay, what is that temperature, guys? In the reading, what's the reading of that temperature? Let me know. You can't say fizzy, no. Why orange? Copper is orange. You just need to know that. Copper is an orange metal. 36, yes, I would say it's 36. The highest one's 36. So the change in temperature is just 36 minus 21. So that's 15. Yes. Could you say copper is formed? No, you can't say copper is formed because it's asking about the observations. So what would you see? You have to say what you would actually physically see, which is an orange metal, which is copper. Cool. Next one. We've got some data here. Teacher repeated the investigation using a digital thermometer. Calculate the value B. We just need to work out the mean, a very common calculation you need to do. Mean is just average. So this is just math. 7.8 plus 7.3 plus 7.7 divided by the total number. What do we have here? 7.6. How do you see a color change? So you see a color change because copper sulfate is blue and it's no longer copper sulfate. It's turning to zinc sulfate, which isn't blue. So you just need to know that basically. Okay, next one. The range of the results is the minimum value of the temperature increased to the maximum value. What is the range? What's the range here, guys? For 2 grams of zinc. So it says, let me look at the question. What is the range with 2 grams of zinc? So they want the middle section here. What is the range of this data? What would you guys say it is? So you just want the lowest and the highest. Yes. So usually you would subtract them. You would subtract the lowest from the highest, but the question's not asking that. The question is just asking you to note down the highest and the lowest and the highest. So you'd say 13.1 and 13.8. One of the results for 3 grams is anomalous. Which one is anomalous out of these ones? What would you say is anomalous out of these ones, guys? Which one would you say is the one that doesn't fit the pattern? It would be the 12.9. Yes. Reason? What would you say for the reason? Because you need a reason as well. 12.9. Because, so you need a second mark here. Don't say concordant. You don't need to say concordant. That only comes up in titration. That word only comes up in titration, which is only for triple. It's too small. Yeah, it's too small. We're smaller than the others. Changes. Ammonium nitrate dissolves in water. The change is endothermic. What piece of equipment uses this change? What was the example that we had, guys? Which one was endothermic out of these ones? Hand warmer, self-heating, or sports injury pack? Sports injury pack. That's the one that needs to get cold, right? So it needs an endothermic, endo, down. You want the temperature to go down. So you want a sports injury pack to have an endothermic reaction in it. Next one. A student investigated the temperature change in the reaction between dilute sulfuric acid and potassium hydroxide solution. Potassium hydroxide solution. So we've got an acid and an alkali. This is a neutralization reaction. And what they're doing here, it looks like they are trying to use Vitcha. What is... No, they're not. This is different. This is different. So they're getting potassium hydroxide in a glass beaker. They're adding the sulfuric acid. They're stirring it. They're measuring the temperature of the solution. And then they're repeating it again with a different solution. A student wanted to measure the temperature with a resolution of 0.1 degrees C. Ooh, interesting. Guys, which thermometer here has a resolution of 0.1 degrees C? How would you work this out? Resolution, I'll tell you what it is. Resolution is the smallest reading you can read off. The smallest one. So what does one increment represent here? So this, for example, one increment, it's going from 20 to 30. There are 10 increments. So it's 1 degree. 1 degree C. That's the resolution of the first one. The second one, guys, what's the resolution of the second one? So the first one is 1 degree C. Per line, you're going up by 1 degree C. What's the resolution of the second one? Yep, answer is D. But what is the resolution of the second one? So you're doing 5. It's going up by 5. You're dividing it by 10. So 0.5. Yes, it's going up in 0.5 degrees. What's the resolution of this one? We're going up by 20. And there are 10. Yes, there's 10 divisions. So it's going up in 2s. This one is going from 20 to 21. So it's going up by 1. And there's 10 increments. 1 over 10 is 0.1. So this one on the right has a resolution of 0.1. The answer here would be D. Well done, guys. Energy is lost to the surroundings during the reaction. What type of error is this? Ooh, okay. What type of error is this, guys? What would you say the answer here is? I know why people are saying random error, but it's not actually a random error. There are all sorts of answers here. It's systematic error. There is something wrong with if there's something wrong with the actual equipment that you're using, it's a systematic error. Because remember, Vitchar, what's the I for insulation? There wasn't any insulation here because they're using a glass beaker. If you're using a glass beaker and you're measuring temperature, a lot of that energy is just going to leave to the surroundings. And every time you do that reaction, you're going to lose energy. So your readings aren't going to be accurate. That's a systematic error. Something wrong with your setup, and that same error is going to occur all the time. Systematic means it's going to happen all the time. A random error is random fluctuations that you can't control. So the room might suddenly get warmer for a little bit or get colder. That's a random error. Systematic is when you have a problem with the experiment itself. Human error is when a human is making a mistake, the person itself, but the human isn't making a mistake here because it's nothing to do with their setup. And zero error is a type of systematic error, but you only get that usually with like mass balances. So zero error is like, imagine you're weighing something on a mass balance, and before you've even put anything on the mass balance, it gives a reading of like 0.5. That's a zero error because it should say zero when you have nothing on it. If it says 0.5 when it should say zero, that's called a zero error. So what we have here is a systematic error, an issue with the setup itself. The student used a glass beaker. Name a container they could use instead of a glass beaker to improve the accuracy of the results. We know this now. Polystyrene cup. Yes. Table 3 shows the results. Okay. Plot the data and draw a line of best fit. So remember, guys, figuring out whether you need a curve or a straight line is important. Let's try and draw this. So 521.2, 521.2. You guys can draw this with me if you want. Next, we have 1022. 1022. Next, we have 1522.8. 1522.8 here. Then we've got 23.6 at 20. So 23.6. 25, 24.4. Over here. You guys can see what kind of line it's going to be, right? 25.2 for the last one. Do you think there's a curved line or a straight line of best fit here? There was a lot of graphs in the biology one. Usually biology is the one with the most graphs, not as much chemistry. Straight line, yes, you can clearly see it's a straight line. And that's what we're going to do, guys. We're going to draw a straight line of best fit here because it's important for the next question. So let's get our ruler. And let's see if you guys are trying this out, see what answer you get for the next question. Straight line of best fit. Let's draw it around. Okay. Let me rotate that a little bit. It's a bit harder for me to move the ruler around. Okay. That's all right. I could do a bit better. Let's do that. And remember, guys, extrapolate it all the way to the end, especially this one. This one, you do need to extend it for the next question. So I think that's a decent line of best fit. The intercept of the y-axis shows the starting temperature of the potassium hydroxide solution. Give the starting temperature. What do you guys think the answer is there then? What's the starting temperature? How do you know it's curved? Like if it looks like that, you can tell like it's curved. You have to judge it yourself. You have to look at your points and see. This was clearly, they were all clearly in a line, so you have to draw a straight line. Yes, 20.5, 20 point, I think my one is around, 20.5, 20.4, something like that. And I'm going to put 20.5. If you guys did that at home yourselves, it says allow a tolerance of half a small square. So I think you can say anything from, so the answer was meant to be 20.4. So you can say anything between 20.3 and 20.5 to get the correct answer. So it's all dependent on how you draw your line of best fit. Okay. Ending in 15 minutes, guys. We're nearly there. Nearly done. 7.7. Another student repeated the investigation, obtained an anomalous result. It was lower than expected. So what will cause this to be lowered? What do you guys think the two answers are here? What do you guys think? Mixture was not stirred. Yes, I'd say that's right. The mixture was not stirred would be one. What else could cause it to not rise to a high temperature? The thermometer was not accurate? No, because the thermometer, they're repeating it and they're using the same thermometer. So you can't say the thermometer was not accurate because only this experiment had the mistake in it. The temperature in the room increased. No, because if the temperature in the room increased, it wouldn't be lower than expected. It'll be higher than expected. So it's not that either. So it's not this, it's not that. Too little sulfuric acid was added. If you add less sulfuric acid, there's going to be less exothermic reaction occurring. There's going to be less energy being released. So the temperature won't go up as high. Give the state symbol. Next question about salts. Give the state symbol for ammonium nitrate solution. Solution, what's the state symbol here? AQ, yes, aqueous. Anything that's a solution is aqueous. Any acid is an aqueous. Any hydroxide is aqueous. What's the formula of nitric acid? Guys, you need to memorize these. Hydrochloric acid is HCl. Sulfuric acid is H2SO4. Nitric acid is HNO3. Okay, memorize those. Ammonia gas dissolves in water to produce ammonia solution. Ammonia solution contains hydroxide ions. Student adds universal indicator to nitric acid and ammonia. What color is observed? What color do you get in nitric acid? What color do you get in ammonia solution, guys? Red for the first one. Yes, yes, yes. Color in ammonia solution is going to be, you could say blue or purple. Yep. Good stuff, guys. We're on the last page and then or last two pages. And then if we have time, we can do some electrolysis questions. Let's see how we do for time. Student gradually added nitric acid to ammonia solution. Which row shows the change in pH? So you're starting off with ammonia solution. You're gradually adding nitric acid. How is the pH going to change? It says it eventually adds excess nitric acid. Which one do you guys think the answer here is going to be? Someone saying B. Not sure about that. No, it's not B. The answer's not B. You're starting off with ammonia solution, yeah? Ammonia, we just said, is going to be blue or purple. So the pH is going to start off very high. pH might be about 12, right? Well, it's probably going to be 10 because that's what it says in the question. And then you're adding acid. As you add acid, it's going to go down, 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 down. It's going to neutralize when you've added the same amount of acid, but then we're adding excess acid. So we're going to make it go down even lower. It's going to go down to 2. So it's going to start off at 10 and it's going to go to 2. The answer is D here. Well done. Calculate the percentage by mass of oxygen in ammonium nitrate. Calculation here. Back to a calculation. What do we need to do here? We want the mass of oxygen. We have NH4NO3. So we want oxygen. We want to find out the MR of oxygen, and we want to divide that by the MR of everything and then times it by 100 to get the percentage. So let's try that out. O3, so 16 times by 3. There's 3 lots of oxygen. Let me make that red because that's the color that we're using. Divided by everything in the green. So that's going to be NH4NO3, which they've given us as 80. We're doing 16 times 3 over 80 and then timesing that by 100. and we get 60%. Well done. You guys have got the answers already. Smashing it. Describe a method to investigate how temperature changes when different masses of ammonium nitrate are dissolved in water. Okay, I will say, I'll save this for you guys because we've already gone through these steps, right? Let me go back to the electrolysis ones because I think they're a bit more important. And if we have time, I can come back to that. So that's for that one, you'd use the Vitscher steps. You'd basically use this, yeah? All right, 10 more minutes, 10 more minutes. I'm going back to topic 4, and I'm going to this question. Okay. Let's see if you guys remember what I said. So this question is about electrolysis. A student investigates the mass of copper produced during electrolysis of copper chloride solution. What type of electrolyte do we have here? Do we have molten or aqueous, guys? And what ions are we going to have here? Tell me. Hate electrolysis. That's why I went back to it, guys. I want you guys to do good in these questions. So what do we have? We have copper. Yes, so Cu2 plus, chloride, Cl minus. It's a solution. It's aqueous, like you guys said. So we've got H plus and we've got OH minus. Which gas is produced at the positive electrode? This is where we use Hauck. What's everyone saying? What do you guys think? At the positive electrode, it's asking. People are saying chlorine. So the positive electrode is going to be one of the negative ones. So let me rewrite the ions again. So we've got Cu2 plus, we've got H plus, we got Cl minus, and we've got OH minus. Positive electrode is going to get one of the negative ones. And the rule is if there's a halogen, the halogen will go. So it's going to be chlorine. Chlorine is going to be the answer there. Well done for you guys. Copper is produced at the negative electrode. What does this tell you about the reactivity of copper? Yes. Guys, why is it copper instead of hydrogen? What's the reason? Why is it copper that gets produced here? What does that tell us in Hauck? So halogen always goes at the anode, and the less reactive one goes to the cathode. So that tells us that, yes, copper is less reactive than hydrogen. Copper is less reactive than hydrogen. Determine the mean mass of copper produced after 3 minutes. I've done this question with my students before, and they make a mistake. Let's see if you guys fall for the mistake as well. What do you guys think the answer is here? People saying 1.8. Yes, it is. It's 1.8. So well done. You didn't fall for the trap. It's asking for 3 minutes. So it basically wants 3 minutes. It wants halfway between 2 and 4. Loads of people just tried to find out X because they just saw the X. That's not what this question is asking. It's asking, what would the number be at 3 minutes? It's between 2 and 4, right? 3 is between 2 and 4. So the answer is going to be perfectly between 1.2 and 2.4. What's in the middle between 1.2 and 2.4? It's going to be 1.8. So the answer here is 1.8. Yes. Calculate the mass X. So the next one asks you to work out X after 5 minutes. So what they've done is they worked out a mean, and the mean is 3.06. So what you do is you add these up, and then you divide it by 3, and you should get 3.06. What you want to find is X. So let's write this down. So it's 3.02 plus X plus 3.01, all divided by 3, and that equals 3.06. 3.06. Okay, we want to work out X. So what you want to do first is move the 3 to the other side of the equation. So 3.06, multiply both sides by 3. Then you want to move the 3.01 to the other side. So you want to minus it. And then you want to move the 3.02. So you want to minus that. And then you'll be left with x. And when you do all of that, you get 3.15. Well done, guys. 3.15 for that one. Next, copper chloride solution used in this investigation contains 300 grams per dm cubed of solid CO2 dissolved in 1 dm cubed. Students use 50 centimeters cubed in each one. Calculate the mass of copper chloride. So what's this question telling us? This question is telling us in this solution, there's 300 grams of copper chloride in 1 decimeters cubed. And we want to work out how much there is in 50 centimeters cubed. So what we need to do first is convert the units. How do you go from decimeter to centimeter, guys? How do you go from decimeter to centimeter? We'll email you the link for this whole recording straight after, but you can stay on this link and you can just rewind back as well. Times by 1,000, times by 1,000. Okay, so let me remind you guys, centimeters cubed to dm cubed, you divide by 1,000, but decimeters cubed back to centimeters cubed, you times by 1,000. So this is basically 1,000 centimeters cubed. So in 1,000 centimeters cubed, we have 300 grams. We want to work out how many grams there are in 50 centimeters cubed. So how do you go from 1,000 to 50? We'll make this the last question, guys. How do you go from 1,000 to 50? You want to divide by 20. Good. Divide by 20. So let's divide by 20 on this side. 300 divided by 20 gives you an answer of what? What's the answer here? 15 grams. Yes, it is. 15 grams is the answer. All right, guys. We'll stop there. That was amazing, guys. Well done. Chemistry paper 2. Okay, chemistry paper 1 is a tough one. You guys absolutely smashed it out of the park. Remember, we're going to give you guys the mark schemes. There's a few questions left. We've done about 90% of them. A few questions left you guys can do if you want. We've got all those extra resources for you guys. We've got a website. I made a video on everything on chemistry paper 1. We've got the bootcamp recording. We've got the cheat sheets. We've got the workbooks. You've got everything you need for tomorrow. So you can do some last minute questions if you want. Get a good solid night's sleep. And I hope it all goes well for you guys. Good luck. Good luck. Remember, you can rewind this. You can watch whatever you want. You can rewatch whatever part of it you want. Practice those more calculations as well. And yeah, next science paper is after half term. So it's going to be a while. So it's going to be physics paper 1. So that's another free one as well. That's going to be taken by Nav, physics tutor. Same setup again, guys. We'll send you guys a workbook. We'll go through the key topics again. And then after that, I hope I can see you guys on paper 2. I won't see you guys in the paper 1 for physics, but for those of you who I do see, yeah, looking forward to seeing you guys for the paper 2s. Revise hard. You're almost halfway through your exams. You're almost halfway through. So keep it going, guys. Okay. Thank you, guys. Honestly, wish you all the best. Let me know how it goes, like on TikTok or something. I really hope it goes well. And I hope I see you guys in the paper 2s. If not, all the best with all your exams. What would you say is the best thing to revise? It depends on what you're not good at. That's what I'd revise. Whatever you're not good at, I would revise. Required practicals are always the big things to revise. So much coming. I'm trying to keep up with everything. What topics haven't been covered? Look at the workbook and you can see. No worries. Thank you, guys. Thank you for the kind comments. Honestly, it's worth it. If you get a chance, write us a review on Trustpilot. That would mean a lot. Yeah, helps us out a lot. Yes, shout out to everyone. I can't see. Sorry, I lost your name. Predictions? No, I don't have any predictions. Sorry, I don't do predictions. I don't know. I would probably get them wrong anyway if I did predicted stuff. I would never risk it with that. I just tell everyone to revise everything. Do I have a video on limiting reactants? Ooh, the recording. Watch the recording. We go through an example on limiting reactants. Definitely go through that and watch the. Yeah, no, go through that. I did that. Abd Ascend, shout out. There we go. Okay, guys. I think I'm gonna head off now. You guys have been amazing. How do you sign up for paper 2? Go back to the website. Go into the link on our bio on TikTok, and you can sign up to our paper 2s. I hope I see most of you guys there. It's going to be the same setup. So if you guys found the paper 1s useful, then definitely come to the paper 2s. It's only £10. It's £2.50 per hour. Yeah, if you guys think it's worth it, definitely. I hope to see you guys there. We've already got loads of sign-ups as well. So yeah, join if you guys are interested. And we'll send you guys all the resources. What tablet? I use an iPad and I use an Apple Pencil. All right, guys, I'm going to head off now. All the best. Do that last minute cramming and hope to hear from you guys tomorrow or see you at the paper 2s. Good luck, guys. Good luck. Good luck. Bye.